Hello everyone. Could you say us if are you asking us?
Sí. Bueno. Sí. Yo. Y luego cuando presento tengo que poner esto. Good morning. Thank you for coming this third day in the MITAC. Our first speaker today is Luis Fernando Mora, and he will be speaking about first and second modules relative to subclasses of proradicals. Bueno, muchas gracias por la presentación y por la invitación. Y una disculpa por no poder hablarlo en inglés, pero vengo algo desvelado y mi inglés puede que sea menos entendible que mi español. Entonces, les voy a presentar un trabajo que estoy haciendo en colaboración con el doctor Hugo Alberto Rincón Mejía y le podemos cambiar a la siguiente. Gracias. ¿Con cuál se cambia de? No cambia de. ¿O como abajo hacia acá? ¿Hacia acá? Ok. Ok, perfecto. Bueno, lo primero solo es recordar algunas definiciones básicas. Un preradical es un subfuntor de la identidad en RMOD. Eso básicamente nos dice que los morfismos que aplicado a un objeto es un subobjeto y los morfismos se restringen y se correstringen bien. Uno de los primeros resultados que se tiene es que conmuta con coproductos. Hacia el otro lado. Bueno, y se clasifican de diferentes formas. Una de ellas, pues, como se puede componer, podemos hablar de indepotencia en la composición y decimos que un preradical es indepotente si compuesto consigo mismo es R. Es radical si sigma de M cociente sigma de M es 0 para todo M en R mod. Es exacto izquierdo si es exacto izquierdo como funtor. Y este radical si su regla de correspondencia es multiplicar por algún ideal en R. Vamos a denotar RPID, RRAD, TRAD, RLER y RLEP a las diferentes clases, ya sea de T-radicales, radicales exactos izquierdos, radicales exactos izquierdos y radicales indepotentes, respectivamente. Bueno, para poder definir un producto en la retícula de submódulos de un módulo dado, Bicap, Kapka y Nemec y Jambor utilizan el preradical beta, que aplicado, beta de NN aplicado 1, es la suma de todas las imágenes de N de los morfismos que van de M en U. Y define el producto de los dos submódulos A, B y DM como A bullet B como beta de A en M aplicado a B. Y a partir de eso nos da una primera definición de módulo primo, tal vez no histórica, pero sí es la que nos propone en ese artículo, que es un módulo es primo si para cualesquiera dos de sus submódulos el producto de ellos igual a 0, implica que alguno de los dos es 0. También tenemos la noción de primo que nos da Vichy. Para Vichy un módulo primo es los módulos para los cuales el anulador del módulo coincide con el anulador de cualquiera de sus submódulos distintos de 0. Y a partir de la definición de primo de Vichy, surgió la idea de dualizar la noción de primo y Yasemi propuso la definición de módulo segundo, que es una idea de el dual de primo, ¿no? Que es el anulador de un módulo coincide con el anulador de cualesquiera de sus cocientes no nulos. Recordando que el anulador es simplemente el conjunto de los elementos del anillo que anulan a todo elemento de M. Ay, me pasa. Entonces, tenemos unas caracterizaciones como básicas de estas tres nociones que tienen que ver con primalidad. Un módulo va a ser BJKN', le voy a llamar así para poderlo diferenciar de primo propuesto por Vichy. Si solamente si, cada uno de sus submódulos, ya voy a apagar esta cosa. Ok. Cada uno de sus submódulos no nulos lo cogenera. Es decir, que el módulo se sumerge en un producto de copias de cualquiera de sus submódulos. Un módulo va a ser primo si solamente si para cualquier ideal bilateral de R y para cualquier submódulo no cero de él. Si I por N cero, entonces I por M cero. Es decir, si anula a cualquiera de sus submódulos, lo anula a él también. Y va a ser segundo si solamente si para cualquier submódulo, no, más bien para cualquier ideal bilateral del anillo, multiplicar a M por I o es cero o es el total. Como observación rápida, un anillo va a ser segundo si solamente si es simple. Segundo como módulo sobre sí mismo. Ok, entonces, siguiendo estas dos ideas, estas dos caracterizaciones de módulo primo y módulo segundo, Abulay propone lo que es una acción de un orden parcial en una retícula de la siguiente forma: es simplemente que conserve o que preserve una función que va del orden parcial cruz la retícula en la retícula, que preserva el orden tanto del orden parcial, ¿sí? Fijando el lado derecho, y el orden de la retícula fijando el lado izquierdo, y que aplicado un elemento del orden parcial a un elemento de la retícula siempre va a quedar por debajo del elemento original. ¿Tienen para apuntar? Ah, sí, perfecto. Ok. Entonces, algo que podemos notar rápidamente es que si tenemos un orden parcial y consideramos un suborden de ese orden parcial, cualquier acción inducida por el primer orden, es decir, por P, va a inducir una por el suborden. Esto nos va a servir más adelante para dar algunas implicaciones. Ahora, si nos fijamos, bueno, él define lo que es dada una acción de un orden parcial P en L, define que un elemento distinto de cero es primero, si siempre que yo le aplique un elemento del orden parcial a cualquier subobjeto de él, cualquier elemento que esté por debajo de él, distinto del elemento mínimo, si nos da el elemento mínimo, entonces también lo hacía con X. Y es segundo si para cualquier elemento del orden parcial, si se lo aplicamos a el elemento X, nos da 0 o nos da el mismo X, que si nos fijamos en la definición de primo y segundo, y nos fijamos que también... Perdón. Ok, ya. Ahora sí ya se pagó. Ok. Si nos fijamos en la primera definición que tenemos de primo y segundo, podemos ver que se puede hacer actuar la retícula de ideales en la retícula de submódulos de un módulo dado, dándonos como resultado justamente, si aplicamos estas dos definiciones a ese contexto, la definición usual de primo y de segundo. Y pues, retomando esto de los preradicales, si nos tomamos una subclase de la retícula de preradicales, esta va a actuar en la retícula de submódulos de un módulo mediante la evaluación. Sí. Ok. Entonces, como un corolario de las que tenemos acciones dado un suborden, si tenemos un orden parcial y una acción, un orden parcial P, una acción de P en L y un Q subconjunto de P, vamos a tener que induce una acción de Q en L, y cualquier elemento P primero o P segundo va a ser un elemento Q primero o Q segundo. Entonces, a partir de eso, pues simplemente podemos hacer la traducción de lo que significa hacer actuar esta subclase de los prerradicales en la retícula de submódulos, y como no depende realmente de dónde esté contenido el módulo para decir si es primero o si es segundo, podemos decir que un módulo va a ser primero si es primero sobre sí mismo, como subobjeto de sí mismo. Y pues adecuar la definición de esta forma, un módulo va a ser A primero con una subclase de prerradicales, ¿sí? Siempre que alfa de K sea 0, eso implica que alfa de M 0 para cualquier K submódulo distinto de 0 de M y para cualquier alfa en A. Va a ser completamente primero. Esta definición nos va a servir en un momento para poder hablar de esta descompuesta en su parte de torsión más esta clase de los completamente primeros. Si alfa de K es distinto de 0 para cualquier K submódulo distinto de 0 de M y para cualquier alfa en A. Una observación inmediata es que los completamente primeros son en particular primeros. Y va a ser A segundo si alfa de M0 o alfa de MSM para cualquier alfa en A. Bueno, aquí unas observaciones rápidas. Si nos tomamos diferentes clases ya conocidas de prerradicales, vamos a encontrar justamente las definiciones que surgieron de tratar de hablar de primalidad en módulos. Por ejemplo, si nos tomamos los RPR primeros, sobre toda la retícula, la retícula de prerradicales, los RPR primeros son justamente los BJKN primos, los descritos por Vicam, Jambor, Kapkan. Y los T radicales, los T-rad primeros, son exactamente los primos, los T-rad segundos son exactamente los segundos sobre la clase de los radicales exactos izquierdos son los mismos que los decisivos que describió Golan en el libro de teorías de torsión, que son los módulos tales que para cualquier teoría de torsión está o en su parte de torsión o en su parte libre de torsión. Los rad segundos son los módulos que son cogenerados por cualquiera de sus cocientes no nulos, y los segundos respecto a los preradicales indepotentes son aquellos que son generados por cualquiera de sus submódulos no cero. Sí, es hacia abajo. Y a partir de estos podemos caracterizar en algunos contextos cuáles son RPR segundos en general, porque pues, para cualquier anillo es un poco complicado caracterizarlos, pero en el caso de los dominios ideales principales, los RPR segundos son los módulos que son semisimples homogéneos o divisibles libres de torsión. En el caso de los anillos exactos izquierdos o perfectos izquierdos, en cualquiera de los dos, los RPR segundos van a ser los semisimples homogéneos, nada más. A partir de estas tres definiciones de A primero, A segundo y A fuertemente primero, se pueden definir clases de módulos de la siguiente forma, ¿no? Esta P caligráfica le vamos a llamar, va a ser la clase de los que son A completamente primeros, la P mayúscula va a ser la clase de los A primeros y el módulo cero, y SDA va a ser la clase de los A segundos y el módulo cero, porque pues nuestra definición descarta el módulo cero como módulo primero, módulo segundo, pero sí podría llegar a ser módulo completamente primero. Y para el caso de cuando tomemos un solo, bueno, el singleton de un solo elemento en los prerradicales, simplemente le llamaremos P sub sigma y S sub sigma. Lo bueno de aquí es que directamente la clase de los que son sigma primeros es la unión de la clase de los sigma fuertemente primeros, unión los que son de sigma libres de sigma pretorsión. La clase de los segundos simplemente se puede ver como la clase de los de sigma torsión, sigma pretorsión, unión la clase de los libres de sigma torsión. Y para el caso de los de la clase de los sigma fuertemente primero, resulta que la clase de los sigma fuertemente primeros es una clase natural. Y como para cualquier clase de prerradicales, vamos a tener que la clase de los sigma fuertemente primeros es la intersección de cada uno de los P sigma con sigma en A, pues para cualquier subclase de los prerradicales, P sub sigma va a ser una clase natural. Entonces, esto nos va a dar no solo una manera de encontrar clases naturales, sino también nos está dando una correspondencia entre la retícula de prerradicales y la retícula de clases naturales, que es un morfismo de retículas. ¿Sí? Es decir, es compatible con la estructura. No abre ínfimos y supremos. Y bueno, podemos ver cuándo es que la clase de los sigma fuertemente primeros es todo remoto, que es justo cuando el radical generado por sigma es cogenerado por sigma, perdón, es la identidad, o cuando la clase libre de pretorsión, de sigma pretorsión, es el cero nada más. Y esto nos da una caracterización de un anillo. Para un anillo es equivalente que el anillo sea producto directo finito de anillos simples, a que la clase de los P sigma sea distinto de R mod para cualquier sigma distinto de la identidad. También tenemos que si sigma es un T radical, no solo P sigma va a ser una clase natural, sino va a ser una clase natural cerrada bajo productos. Entonces, naturalmente, igual por lo de las intersecciones que tenemos, si tomamos una clase de T radicales, P de esa clase va a ser cerrado bajo productos, lo que nos da una caracterización casi inmediata de los anillos semiartinianos izquierdos. Por ahí existe un resultado que dice que un anillo es semiartiniano izquierdo si las clases naturales son cerradas bajo productos. Entonces, justamente podemos caracterizarlos, en este caso sí vamos a necesitar la restricción de que el anillo sea conmutativo, el anillo va a ser semiartiniano izquierdo si cualquier clase natural se puede ver como el P de alguna clase de T radicales. El 2 implica 1 siempre se da, el 1 implica 2 sí requiere de conmutatividad. Ok. Y pues podemos ver condiciones un poco más globales. Si, por ejemplo, sobre toda la retícula radicales, todos los módulos fueran RPR primeros, entonces el anillo sería semisimple local izquierdo. Pasa lo mismo si nos fijamos en los anillos en los cuales todos los módulos son son segundos respecto a los prerradicales indepotentes, o segundos respecto a los radicales, o segundos respecto a todos los todos los prerradicales. El anillo va a resultar ser otra vez un anillo semisimple local izquierdo. Es decir, pues el anillo es copia del simples isomorfos entre sí. Y pues nada más quiero recalcar ahí una parte que creo que no compile bien. Por aquí está. Esto ya en cierta forma nos está diciendo, sumado al teorema de que si tomamos una subclase, más bien un suborden de un orden dado, los primeros se traspasan bien entre orden y orden, nos estaría diciendo básicamente que de aquí se sigue de manera inmediata que los BJN primos son primos, que los RPR segundos son tanto segundos como decisivos, pero los regresos no se dan. De hecho, los RRAT segundos van a ser también TRAT segundos y segundos sobre la retícula de radicales exactos izquierdos, es decir, los RRAT segundos van a ser tanto decisivos como segundos, pero los regresos no se valen, los segundos no son RRAT segundos y los decisivos tampoco son RRAT segundos. Entonces, esta forma de tratar con subclases de prerradicales sí nos está dando nuevas condiciones de primalidad en ese sentido. ¿Sí? Podemos estudiar a partir de alguna clase específica de prerradicales estas dos nociones ya trasladadas a esa subclase. Y bueno, como bibliografía, pues agregué todos los artículos que utilizamos para esa parte. Y pues sería todo por mi parte. Gracias por su atención.
Thank you. Fernando, is there any question? Adelante.
Hola, dijiste que las clases de primos respecto a una clase cualquiera de radicales es natural, ¿verdad?
Sí.
Suena como que abarcas muchas clases naturales. ¿Hay alguna idea de si eso puede abarcar todas las clases naturales? Bueno.
Hay por ahí un artículo del doctor Alejandro Alvarado, me parece que con el doctor Hugo Rincón, y no recuerdo quién más estaba en ese artículo, que describen unas clases que, dado un preradical exacto izquierdo, es la clase de los módulos, tal que sigma aplicado a ese módulo es esencial en él. Demuestran que esas clases son clases naturales y justamente le llaman esa retícula retorsa. Resulta que estas clases de prerradicales fuertemente primeros, para cualquier preradical exactamente, para cualquier preradical podemos encontrar una clase de ese estilo que sea igual a la clase de los fuertemente primeros. Y en ese artículo viene justamente caracterizado el cuando es toda la retícula de clases naturales, que es justamente cuando el anillo es semiartiniano izquierdo.
Ok, gracias.
Anyone else? ¿Alguien más? Por allá hay un.
Sí, gracias. En el mismo sentido que mencionaste que le pegas a las clases naturales, oye, si no mal recuerdo, las clases naturales forman una retícula booleana, ¿no? Entonces, ¿qué pasa con el complemento si también proviene de una de estas?
De hecho, lo que se puede ver como, o sea, se puede demostrar de dos formas que de aquí es una clase natural. Una es respecto a las clases más bien las propiedades de cerradura, se puede mostrar bastante rápido, o también se puede notar que es el pseudocomplemento de la clase libre de sigmatorsión. Entonces, se tiene justamente ese resultado, que las clases naturales es el esqueleto de las clases hereditarias. Entonces, se comportan bien en ese sentido, pero en este otro sentido, no tanto porque justamente en la retícula de prerradicales no siempre tienes complementos. Entonces, no se van a trasladar bien como de ida y de regreso, porque justo acá hay complementos porque es una retícula booleana, pero en el caso de los prerradicales se tiene demostrado que que están pseudocomplementados. Pero para que existan complementos sí se requiere, creo que inclusive que el preradical sea exacto. Entonces sí se puede como restringir de cierta forma para que los complementos sean como compatibles, pero es hacer muy, muy chiquita a la clase de prerradicales.
Gracias.
Bueno, ya que estás mencionando la función esta, ¿hay algún caso en que esta función sea inyectiva? Bueno, esa asignación, perdón.
De hecho, lo que tenemos bien caracterizado todos los que van al mismo. O
Ok,
sea, de hecho,
la fibra de
sí,
cada clase
exactamente.
natural.
Sí, entonces lo que podemos hacer o lo que se puede hacer es directamente tomar los exactos izquierdos y eso sí va a ser,
Eso sí se sumerge.
sí se sumerge bien en la clase de retículas naturales. De hecho, pues justo con esta misma idea de que estos de acá son los pseudocomplementos de estos de aquí. Entonces, justo todos los que tengan como la misma clase, eh, la clase de torsión generada por la clase de pretorsión de f de sigma van a ir al mismo lugar. Entonces ya con eso sí se puede como restringir bien para que sea inyectiva.
Gracias.
Después. Ok.
Sí.
Ok.
Bueno, muchas gracias por invitarme y muchas gracias.
Let's take our speaker.
Muchas gracias.
Next talk is in about 2 minutes.
Pero cuando le das a partir ya aparece.
Es este, ¿no?
No, no se ve.
Es-
Ajá, sí.
Our next speaker is Luis Donaldo Arreola. His talk is BKN Rings, a study of non-zero homomorphisms. Thank you.
Gracias. Buenos días a todos. Antes que nada, gracias a los organizadores por la invitación y por aceptarme la plática. Bueno, en esta media hora voy a platicarles un poco de un pequeño trabajo que hicimos en el doctorado con mis directores de tesis, el doctor Gerardo Reina Hernández, el doctor Iván Fernando Vilches Montalvo y la doctora Marta Lisbeth Shade Sandoval. Bueno, la charla tiene por título Anillos BKN, un estudio de de homomorfismos no cero. Bueno, en este trabajo lo que nosotros hacemos es estudiar anillos que satisfacen la propiedad de que para cualquier par de R-módulos, ya sean izquierdos o derechos, ya sea el caso, siempre existe al menos un homomorfismo no trivial entre este par de R-módulos. Y bueno, se reciben el nombre de BKN, anillos BKN. Y lo que tratamos de hacer es establecer conexiones entre ese tipo de anillos con otros que pues tienen propiedades muy parecidas, como los anillos retráctiles, los completamente corretráctiles, y los anillos conmutativos, y casos especiales de módulos. Y bueno, antes que nada, la motivación de este estudio. La propiedad de que exista un homomorfismo no trivial entre un par de módulos para módulos especiales, pues ya ha sido estudiado en varios trabajos. Por ejemplo, en la siguiente cita, los Troley y colaboradores estudian los anillos retráctiles, que son anillos que satisfacen la propiedad de que siempre existe al menos un homomorfismo no trivial entre un par de módulos, con la condición de que el segundo sea un submódulo no cero del primero. Y en la siguiente referencia, a mini colaboradores estudian el caso dual, anillos completamente corretráctiles, y que son anillos que satisfacen que el OM entre dos módulos es no trivial, pero con la condición de que el primero sea un cociente del segundo y el divisor sea un submódulo propio del segundo. Y bueno, también se han estudiado casos de anillos que satisfacen la existencia de homomorfismos no triviales para módulos no inyectivos y también para módulos no proyectivos. Y bueno, el caso más general, cuando solamente le pedimos a los módulos que sean no triviales, que no sean cero, perdón, pues es menos conocido. ¿Sí? Aunque ya hay una caracterización que data del año 1982, que aparece en un libro publicado por Vican, Kepke y Nemec. Y pues inspirados en esta caracterización, en el 2017, Rincón Mejía y colaboradores proponen la siguiente definición en esta referencia. ¿Qué dice lo siguiente? Un anillo R se define como anillo BKN izquierdo si satisface que el OM entre dos módulos no cero, pues siempre es no trivial. De la misma manera se definen los anillos BKN derechos. Y si un anillo satisface ser tanto BKN izquierdo como BKN derecho, pues vamos a decir que el anillo es simplemente BKN. Y después aparece la caracterización de ese tipo de anillos con términos más nuevos, como la siguiente referencia, Vilches Montalvo y colaboradores demuestran que un anillo R debe ser, es BKN izquierdo, sí, solo sí, el anillo es local izquierdo, simertinén izquierdo y más izquierdo. Y bueno, voy a hablar un poquito de la demostración, pero antes voy a mencionar qué significan esas tres propiedades. Decimos que un anillo R es local izquierdo si solamente en la categoría de R-mod existe un R-módulo simple bajo isomorfismo o bajo isomorfismo, ¿no? Un único. Decimos que el anillo R es semiardineno izquierdo si todo R-módulo no cero, M, tiene pues al menos un simple, ¿no? O que su soclo es no cero. Decimos que el anillo es max izquierdo si todo módulo izquierdo tiene pues un cociente simple. Y entonces la caracterización que decíamos dice lo siguiente: un anillo R es BKN izquierdo si solo si es tanto local izquierdo como semiardineno izquierdo y max izquierdo. Y el esbozo de la demostración pues es más o menos como sigue. Pues suponemos que el anillo es BKN izquierdo, entonces si nosotros tomamos dos simples, pues como es BKN izquierdo, pues existe al menos un homomorfismo entre ellos, el cual forzosamente tiene que ser un isomorfismo, así que todos los simples son isomorfos, así que el anillo es local izquierdo. Si ahora tomamos un simple y tomamos un módulo, pues solamente pidiéndole que no sea cero, debe existir un homomorfismo en ambas direcciones. El que va del simple al módulo M, pues tiene que ser un monomorfismo, ¿no? Y el que va del arbitrario, que no es cero, al simple, pues es un epimorfismo. Y bueno, pues ya con esto decimos que el anillo tiene que ser semiartiniano y match izquierdo respectivamente. Y pues para el regreso, si suponemos que es tanto local como match y semiartiniano izquierdo, pues al ser match, pues debe existir de un módulo, debe existir, debe tener un cociente simple. Tomamos como alfa, pues la proyección hacia ese simple, hacia ese cociente, y tomamos otro módulo arbitrario no cero n, y pues como todos los simples son isomorfos, podemos decir que es el mismo, ¿no? Pues ese también se sumerge en n, perdón. Y la composición de estos dos homomorfismos es un homomorfismo no trivial entre m y n. Así que el anillo es BKN izquierdo. Bueno, cosas inmediatas es que en un anillo BKN izquierdo, todos los módulos inyectivos izquierdos van a ser cogeneradores inyectivos. Y bueno, estudiando la relación entre los retráctiles y los BKN, pues recordemos que un anillo es no retráctil si decíamos que el ohm entre dos módulos es no cero, con la condición de que pues, el segundo sea un submódulo no cero del primero. Y tenemos el siguiente resultado, que dice lo siguiente: las siguientes propiedades son equivalentes para un anillo R. Primero, tenemos que el anillo es no retráctil izquierdo y que cada inyectivo no cero pues va a ser un cogenerador. Y equivalente a que el anillo sea match izquierdo y que cada inyectivo no cero pues sea un cogenerador. A su vez, esto es equivalente a que el anillo sea, sea BKN izquierdo. Y por último, a que pues, en la categoría de remote no haya teorías de torsión no triviales. El esbozo de la demostración va más o menos así. Si suponemos primero que el anillo es no retráctil y que cada inyectivo es un cogenerador, vamos a demostrar que el anillo es más izquierdo y que, pues lo mismo, ¿no? Que cada inyectivo es un cogenerador. Eso ya está dado, ¿no? Pero bueno, vamos a suponer que el anillo es no retráctil. De teoría se sabe que el no retráctil implica match. Así que pues ya está la 1 implica 2. Si suponemos que ahora el anillo es match izquierdo y que además todo inyectivo es un cogenerador, vamos a demostrar que el anillo es BKN. Si tomamos dos módulos no cero izquierdos, entonces existe pues un simple que va de, perdón, este M va a tener un cociente simple, llamémoslo S, y pues ese epimorfismo que va de M hacia su cociente lo vamos a denotar con F. Y ahora si tomamos a N y su cápsula inyectiva, como todos los inyectivos son cogeneradores, pues tenemos que el ohm entre el simple S y la cápsula inyectiva pues va a ser no trivial, ¿no? Porque pues la cápsula es un cogenerador. Y pues entonces tomando el encaje que hay de S en la cápsula inyectiva y tomando a F, ¿sí? Que va de M al simple, pues tenemos ahí una composición que nos da un homomorfismo no trivial entre M y N. El anillo es BKN. Bueno, si ahora suponemos que el anillo es BKN, pues vamos a demostrar que no hay teorías de torsión no triviales en R remoto. Si tomamos una teoría de torsión en R mod y tomamos un módulo no cero en T y uno en F, pues entonces el ohm entre los dos tiene que ser distinto de cero, ¿no? Perdón, aquí era igual, el ohm entre ellos dos es cero, y pues como el anillo es BKN, pues esto implica que N tiene que ser cero, ¿vale? No le queda de otra. Y así que pues F, y era F garigoleada, pues es trivial, no es cero, y T tiene que ser la clase también de la garigoleada, una disculpa, es la clase de todos los R módulos, así que la teoría de torsión es trivial. Y lo mismo pasa si tomamos ahora a M en F, ¿no? Y bueno, si ahora suponemos que no hay teoría de torsión, vamos a demostrar que el anillo es no retráctil y que todo inyectivo es un cogenerador. Pues si tomamos un inyectivo, ese inyectivo debe cogenerar una teoría trivial. Eso demuestra que el inyectivo tiene que ser un cogenerador, ¿vale? Y además de, pues, de bibliografía, llegamos rápidamente a que el anillo es retráctil. Y bueno, también estudiamos, decíamos, la relación con los completamente corretráctiles, que recuerdo, son anillos que satisfacen que siempre es posible encontrar un homomorfismo no trivial entre dos módulos con la condición de que el primero es un cociente del segundo y el divisor es propio del segundo. Y pues tenemos aquí un resultado que dice lo siguiente: las siguientes afirmaciones son equivalentes por un anillo R. El anillo es BKN izquierdo, es equivalente a que el anillo sea completamente corretráctil izquierdo y local izquierdo. A su vez, a que el anillo sea BKN derecho, ¿sí?, del otro lado, y que el anillo sea completamente corretráctil derecho y local derecho. Entonces, aquí la importancia de este resultado es que nos da la simetría en la lateralidad de la propiedad BKN. Pues, entonces, de aquí en adelante da lo mismo decir que el anillo es BKN izquierdo a decir que el anillo es BKN derecho. ¿Sí? Y bueno, entre otras cosas que hemos hecho, estudiamos su relación con el funtor cambio de anillos, que pues se define de la siguiente manera: si tenemos un homomorfismo de anillos unitario entre dos R y S anillos, pues lo que hace el funtor cambio de anillos es pasar de la categoría de S mod a R mod. Y pues de la siguiente manera, ¿no? Si tomamos un S módulo M, lo que hace el funtor es tomar el mismo grupo subyacente de M, perdón, lo va a tomar como el grupo para la imagen de M bajo el funtor cambio de anillos. Y la siguiente regla nos da pues la acción, ¿no?, de R sobre ese grupo subyacente a M. Y si tomamos ese homomorfismo, pues la siguiente regla nos lo convierte en un R homomorfismo. Y así que pues cada ese homomorfismo es un R homomorfismo. Y estos grupos pues está uno dentro del otro, ¿no? Y cuando el homomorfismo de anillos es proyectivo, perdón, es sobreyectivo, entonces pues los dos grupos coinciden. Y bueno, tenemos el siguiente resultado. Si tenemos el homomorfismo de anillos unitario entre R y S, y además el funtor cambio de anillos resulta ser pleno, entonces el anillo va a ser y el anillo pues, de partida es BKN, entonces el anillo de llegada también va a ser un anillo BKN. ¿Sí? La demostración va más o menos así: si tomamos dos módulos izquierdos no cero, S módulos, ¿sí?, izquierdos no cero, pues las imágenes bajo el funtor cambio de anillos, pues van a ser también R módulos izquierdos no cero. Y bueno, dado que el anillo lo estamos suponiendo, R lo estamos suponiendo como BKN, pues existe un homomorfismo no cero entre las imágenes de M y N, perdón, bajo el funtor F. Y por hipótesis, pues debe existir un homomorfismo, ¿no? Un S homomorfismo de M a N, porque pues el funtor es pleno. Y debe ser la imagen de G. F debe ser la imagen de G bajo el funtor cambio de anillos. Y dado que pues F es no cero, G también tiene que ser no cero. Y como corolario, pues decimos que si ρ es un homomorfismo unitario de anillos sobreyectivo, y pues en R también es BKN, resulta ser también que ese es BKN. Y pues dado que si tomamos dos S módulos M y N, tenemos que los ohms coinciden, ¿no? Como S módulos y como R módulos coinciden porque pues el funtor, perdón, como el homomorfismo de anillos es sobreyectivo. Así que el funtor cambio de anillos resulta ser pleno y pues siguiendo el teorema anterior, pues ya terminamos. Otras cosas que se encontraron es que en la situación de este corolario, si la imagen del anillo S es proyectivo, resulta ser que R y S son anillos Morita equivalentes. Y como corolario, igual, en la misma situación del corolario 1, si Q es la imagen de S bajo el puntual cambio de anillos y existe un homomorfismo, R homomorfismo entre esa imagen de S bajo el puntor y R, que preserve las unidades, pues entonces también los anillos tienen que ser Morita equivalentes. BKN Morita equivalente. Y bueno, algo que mencionar es que la relación con el producto tensorial. Tenemos este isomorfismo muy conocido del producto tensorial que nos da la siguiente propiedad, que si R es un anillo BKN, entonces el producto tensorial entre dos módulos, uno R módulo derecho, el otro un R bimódulo, y ambos no cero, pues siempre el producto tensorial va a ser no cero. Y bueno, con los anillos conmutativos, pues resulta ser que las nociones de semiartinianidad y de morretractibilidad son equivalentes, ¿sí? Coinciden, así que pues en los anillos conmutativos, así que pues nos da inmediato este resultado que es similar al teorema 2, pero ahora particular para anillos conmutativos, que dice lo siguiente: en un anillo conmutativo R se tiene que el anillo es muy retráctil, que cada inyectivo es un cogenerador, equivalente a que el anillo sea semiartiniano, que cada inyectivo sea un cogenerador, que el anillo sea MATS, y que cada inyectivo sea un cogenerador, que el anillo sea BKN y que también no haya teorías de torsión no triviales en R-mod. Y bueno, también en los anillos conmutativos se tiene las siguientes tres equivalencias. ¿Tengo tiempo todavía? ¿Sí? ¿Sí? Ah, ok. Ajá, primero que si tenemos dos R módulos no cero, pues el producto tensorial es no cero, y equivalente a que el anillo sea local y que haya solamente un único ideal máximo, digamos J, tal que pues para cada R módulo M, si resulta ser que M es dicho ideal por M, entonces ese módulo M tiene que ser cero. Y equivalente a que el anillo sea BKN. La demostración va más o menos así. Pues resulta ser que si tomamos dos ideales propios de R, el producto tensorial de los cocientes es isomorfo al anillo cociente de la suma de los ideales, ¿vale? Entonces resulta ser que como pues esto no es cero, pues esto obliga a que pues, la suma de dos ideales propios siga siendo propio. Pues demostramos que pues el anillo tiene un único ideal máximo, ¿sí? El anillo es local y después, si suponemos que hay un módulo M con esta propiedad, pues como este ideal J es el único ideal máximo, ¿sí? Este producto tensorial tiene que ser cero. Y pues este no es cero, porque es lo que hace que JM sea cero. Así que M tiene que ser cero. Y bueno, para demostrar 2 implica 3, es suficiente comprobar que el anillo es semiartiniano y MATS. Y bueno, usando un poco de algunos resultados que hay ahí en la teoría de módulos, llegamos a que dicho J, dicho ideal máximo J, resulta ser tenilpotente y este cociente R sobre J tiene que ser semisimple. Y al ser semisimple también demostramos después que el anillo tiene que ser perfecto y la perfectitud le da la condición de ser max. Y bueno, esto también de algún resultado por ahí de las referencias también nos da que el anillo tiene que ser semiartiniano y pues con eso ya tenemos que el anillo es BKN. Y bueno, la implicación 3 implica 1, pues es más rápida, ¿no? Usando la proposición 2. Y bueno, son algunas de las cosas que hicimos en ese trabajo. Sí, y pues por mi parte sería todo. Aquí hay unas referencias que hemos usado. Gracias.
Is there any question? Luis. Yo tengo una. ¿Un anillo BKN no tiene que ser simple, homogéneo? Semisimple, homogéneo.
Semisimple homogéneo. No, hay hay algunos anillos que satisfacen. Hay un ejemplito que no puse, más o menos no me acuerdo bien, pero tomamos un campo y construimos un anillo con matrices infinitas con una cantidad mínima, una cantidad finita de entradas no cero, tomadas arriba de la diagonal, y esas entradas tomadas en un campo. Resulta ser que este anillo no es no es BKN y no es semisimple. Como que
Pero todo BKN sí es anillo simple, ¿no? Sí, no tienen ideales bilaterales.
todo BKN, perdón,
¿Es anillo simple? O sea, que no tiene ideales bilaterales.
mm,
Me surgió por lo de que no hay teorías de torsión. No sé
ajá.
si eso implica que no haya ideales bilaterales.
Me parece que sí.
um,
¿No? Es que si no hay teorías de torsión, pues mi pregunta es si entonces no hay ideales bilaterales. Que cada ideal bilateral te genera
ajá.
te podría generar, pero
Sí,
o no estoy mal.
de momento no tengo la respuesta. Sí, pero queda
Gracias.
buena pregunta para analizarlo. Sí,
Well,
gracias.
no. Let's think again. Please. See if another question. Oh, thank you.
¿Vale? Ah,
Ready?
Yeah. Todo desmañanado.
Let's continue with the workshop given by Sebastian Melzer. Thank you.
Thank you. Hi, everyone. So this is my last talk, so I hope we can see some more deep results or results more related to my research than what we have seen so far. But before I go there, let's talk again about what we have done so far. So the first talk was about the background, point field topology, stone LG spectral spaces, a bit about Priestley spaces, and then in talk 2, we went into a Esaki duality and a Priestley duality for frames. And we started talking about some of the aspects of point field topology in the language of Priestley spaces, especially speciality and sublocales. So, I mean, basically I did this slide just now, but yeah, last time we discussed the properties of Priestley space of frames specifically. We saw that they are Esaki spaces that are extremely order disconnected. We introduced this thing that I call the localic part of an L space that corresponds to the space of points of the frame. And this is related to speciality and also sobriety, if you don't start with a sober space. And finally, we talked about nuclear subsets and we gave this kind of sketch of how to prove Isbell's density theorem in this setting. And now I want to talk about compactness and continuity. So I want to define this relation. I hope you have seen this relation before. It's the way below relation. It basically means in a frame, A is way below B. Whenever B is below some join, A is below a finite join of elements in that set. So how does this look like in a Priestley space? We have that A is way below B if and only if. So phi was the stone map, so it's the isomorphism between the frame and the Clopen upsets of the Priestley space. So A is way below B if and only phi of B whenever it's inside the closure of some. So U should be an open upset. I forgot to write it here, but if phi of B is in the closure of an open upset, phi of A should be inside the open upset. So if A is way below B, its Clopen upset should always go inside these open upsets whenever phi of B sits inside the closure. I wanted to give a sketch of this, at least in one direction. So suppose A is way below B and phi of B sits inside the closure of some open upset. If U is an open upset, it's the union of Clopen upsets. That's one of the properties of Priestley spaces. So we can write Clopen upsets in this form, phi of some element of my frame. So I have some set in my frame, its image, and then the union will give me that open upset. So in other words, phi of B sits inside the closure of the union. But that is exactly what it means for B to sit inside the join of S. But because B is way below A, or A is way below B, A sits inside some finite subset, sits inside the join of some finite subsets, and then if I translate it back to my Priestley space, I get that phi of A sits inside a finite union of Clopen upsets. So then for my join, I don't require the closure anymore inside the Priestley space because finite unions of Clopen upsets are still Clopen upsets. And this thing sits inside this one, and that is U, well, without the closure. So that's why it goes inside. The other direction is very similar to this, so I will skip that one. So I want to define compact elements in this language. So an element is compact if it's way below itself. So whenever it's below an arbitrary join, you can make that join finite. That's what it means to be compact. Frame is compact if its top element is compact. How does this look like in the Priestley space? So if I have a compact element, it means that the minimum of phi of A sits inside the localic part. So let's see how why that happens. If A is compact, and I take an element in the minimum of phi of A, I want to show this is inside the localic part, so that means I need to show its downset is clopin. That's how I define the localic part. So because the is closed, I just need to show that the downset is open. That means I need to show that the complement is closed. Right, I'm going to show the complement is closed instead of showing that the downset is open. For that, I will show that this difference is empty. So that would mean that they're equal, so that would mean that U is closed. So suppose I have something in this difference, I'm going to show that that gives a contradiction. So if Z is inside the closure of U, let me see what I did here now. Oh, if Z is inside the closure of U but not in U, specifically if Z is not in U, that means it's not in this, so it is inside the downset of X. So that is why it is in the downset of X. So Z is below X, which gives that X is in the closure of U, because the closure of U is a clopin upset. If Z is in there, then anything above it is in there. So X is in the closure of U. But then, because of how I define the closure of U, and because X is in the minimum, it contains all the other points of the minimum, but it also contains X, because X was in the closure. Right? This complement contains everything in the minimum of phi of A except X, because other points in the minimum of phi of A will not be below X. So this closure of U will contain the whole minimum of phi of A, but the upset of minimum of phi of A is phi of A. So the whole of phi of A sits inside this. But now remember the previous lemma that says that if A is way below A, then I can pull phi of A inside the closure. So I get phi of A is inside U. But now X is in phi of A and X is in U. There's a contradiction because X is not in the set. So we assume this and this doesn't happen, so U is closed. So this is exactly what it means for an element to be compact. Its minimum sits inside the localic part. Oh, well, I did only one direction, right? Okay, let's prove the other direction. Suppose the minimum sits inside the localic part. By the lemma we had before, we just need to show that if phi of A sits inside the closure, then phi of A goes inside. So suppose it's inside the closure. What do I have then? If I intersect it with the localic part, then it also sits inside U closure intersected with the localic part. I just intersected the localic part on both sides. But last time we had this lemma. If I have an open upset U and I intersect with the localic part, it doesn't matter whether I take the closure. Localic parts go in, they travel between. Localic points don't care about closure. So I can just write this equal to U intersection Y, but U intersection Y sits inside U. So now I have that phi of A intersection Y sits inside U. But phi of A is the upset of min of phi of A, and min of phi of A is inside phi of A intersection Y, because of my assumption that min of phi of A was inside the localic part. So this is all equal, and this is inside U, so phi of A is inside U. That's what I wanted to show. So now we have this lemma. A is compact if and only if its minimum sits inside Y. Now, if you paid attention, then, okay, I'm going ahead of myself. So because the frame being compact just means that the top element is compact, we can just apply this lemma to 1. And phi of 1 is just X. So L is compact if the minimum of phi of 1, which is min of X, is inside the localic part. So that is what it means for frame to be compact. The minimum of the Priestley space sits inside the localic part. And this is why this happens from the lemma. Now, this is what I wanted to say. In my proof, I really didn't use that phi of A is clopin. So you could have done this whole proof for closed upsets. So what we have is, if I have a closed upset K, these two things are equivalent. Minimum of K is like the localic part, and whenever minimum, and this should just say K, by the way. If K sits inside the closure of U, then K goes inside U. Those two things are equivalent. So what does that mean? And in pre-seriality, you have this correspondence between filters and closed upsets. So filters of my frame correspond to closed upsets of my Priestley space. So closed upsets with this property, one of these two, there will be some kind of special filters, and I want to know what kind of filters. Well, they have to do with compactness. So I guess I already said all this. This is the theorem you have in Priestley spaces. The poset of filters is isomorphic to poset of closed upsets of the space. And I want to look at what filters correspond to these upsets. If you're familiar with Hoffman-Mislov, it would not be that surprising because this was some kind of compactness condition. And filters that we associate with compact sets, they're Scott-open filters. So whenever Scott-open filters are those that whenever there's a join inside, you can make that join finite. And you also might have seen this in another way, that if you have a directed join, then one of the elements is inside of it, that's equivalent. So what happens is that if I have a filter and I look at the dual closed upset, F is Scott-open if and only if the min of K sits inside the localic part. So Scott upsets, what I call them, they're exactly the Priestley version of Scott-open filters. When you move on in this direction, or I guess I keep forgetting what's on my next slide. So at one of my talks, I made this picture to represent a Scott upset. I find it a funny picture, so that's why I want to show it. But if this is my space, X, inside of it I have the localic part. And a Scott upset is one that it's a closed upset and the minimum sits inside of the localic part. So why do I find this picture funny? Because it kind of looks like an egg. Right, you have the egg and you have the egg yolk and it's even Y. But I mean, that is just something that I find funny. You don't have to find it funny. But what you can do with the correspondence between Scott-open filter and Scott upsets is that you can give a proof of Hoffman-Mislov, the Hoffman-Mislov theorem, through the language of Priestley spaces, through Priestley duality. So let me just remind you what the Hoffman-Mislov theorem is. There's two different versions, one phrased for frames, one phrased for sober spaces. I will phrase it for frames. Give a frame L, and let Y be its space of points. Then the open filters of L, the poset of open filters of L is isomorphic to the poset of compact saturated sets of Y. But if you compare this to this theorem, you saw that in a Priestley space, the filters are isomorphic to the closed upsets. These two things kind of look similar. Someone once told me that that this theorem smells like Hoffman-Mislov. I always find it funny to say that it smells like it. I don't know how do theorems smell like. So I'm not sure what smelling like a theorem means, but that's what I've been told. But this was actually a good intuition that these two theorems are similar, because you can prove one from the other. Sorry. So I have a paper on this, but I will just give you the gist of it. If I have this Priestley theorem that the filters of a lattice are isomorphic to the closed upsets, so if my lattice in this case is a frame, what I can do is, what I use this restriction that I just showed, that you can take the open filters and the Scott upsets of the Priestley space. And what you then show is that the compact saturated sets of the localic part correspond to the Scott upsets of the Priestley space. And then you see here I have from open filters of my frame to compact saturated of the localic part, which remember is the space of points. So this gives me Hoffman-Mislov. And if I want to go the other way, I have a lattice and I want to show that the filters of this lattice correspond to the closed upsets of the Priestley space. I apply Hoffman-Mislov to the spectral space because the spectral space is a sober space. So I can say by Hoffman-Mislov that the compact saturated sets of the spectral space are isomorphic to the poset of open filters of the frame of the spectral space. What you then observe is that the compact saturates of the spectral space are exactly the closed upsets of X. And on the other side, you observe that the open filters of the frame of the spectral space are exactly the filters of my lattice. So that's how you go from Hoffman-Mislov to Priestley. Something that I realized later is that the Hoffman-Mislov theorem is equivalent to the prime ideal theorem. And Priestley duality is also something that is equivalent to the prime ideal theorem. So it is not that surprising that these two will be equivalent, because they're both essentially equivalent to the prime ideal theorem. Something that I just noticed when I started talking is that the previous section was called compactness and continuity, and this one is called continuity and regularity. I guess I didn't really talk about continuity in the last section, but I introduced the way below relation. So that's why now I really start talking about continuity. Because what is a continuous frame? It's a frame where every element can be written as the elements way below it. So it's this kind of joint density of some special kind of elements below. If you look at the lemma we had, A is way below B if and only if this happens for open upsets, you can translate way below into the language of the open upsets and then define some kind of map. This map I call, for this talk, I call it con because of continuity. So you have a map from open upsets to open upsets, which is defined like this. The con of a open upset is the union of all the open upsets that are way below. And way below in open upsets means it satisfies this. And I call con dense if for every open upsets, the closure of con is equal to the open upset. And what you then show is that L is continuous if and only if con is dense in its Priestley space. And this is not that hard because you can translate this directly into the language of the Priestley space and it will be essentially this condition. So it's quite a direct translation of what it means to be continuous. But I like to talk about these maps because they will show up a lot. And you can characterize other things with it. For example, I want to talk about stability. Remember, a frame is stably continuous if whenever A is way below B and C, it's below the meet. So it tells you that way below behaves goodly with meet. And it's stably compact if it's also compact. But what you say is that L is stably continuous if this con is dense, because that's what I need for continuous, but it also preserves intersections, binary intersections. So I call that wedge homomorphism. So this con, the stronger it is, the more properties I get on my frame. What else you can say is that, so we saw that L is compact if min X sits inside Y, but there's another characterization like this. L is compact if con of the whole space is still the whole space. In other words, if con is a bounded homomorphism, right, it preserves top. So L is stably compact if con is dense and it's a wedge one homomorphism. Right, and that's how you do these kind of things in the language of Priestley spaces. It's one way, there are other ways. I find this very interesting I will show that in the end, but I find this very interesting. But the reason is that there's all these other maps. So I showed you last slide that L is commutative con X is X, but This is actually true for every element in my frame. A is compact if con of the clopin upset is still the clopin upset. If they're fixed point of cons, then A is compact. But remember that, so these are clopin upsets, and they were compact if they're minimus inside the localic part. That is what it means to be a Scott upset. So these compact elements correspond to clopin Scott upsets. And what I define with clopin Scott upsets is this map AUG. So the AUG of U is the union of all the clopin Scott upsets below it. So essentially the fixed points of con. And if you remember what algebraic is, it's that every element is the join of compact elements below it. So fixed points of the way below relation. So that's the connection there. Frame is arithmetic if binary meet of compact elements is again compact. And it's coherent if it is compact. So this is very similar to with this chain we had from continuous to stably compact. It's just in the setting of algebraic frames. So algebraic frame plus stable plus compact. And we get a similar theorem for this AUG map. Else algebraic if AUG is dense, else arithmetic if AUG is dense in a wedge homomorphism, else coherent if AUG is dense in a wedge 1 homomorphism. So con lets me talk about continuous frame and AUG lets me talk about algebraic frames. And we can also talk about regularity in the dimensional in this way. The regular part of a clopin upset, you just collect all the clopin upsets whose downset is still contained. And the zero-dimensional part is you collect all the clopin bisets, that means their up and downsets that are contained. And you can prove this, that clopin bisets are the fixed points of the regular part. And then we get this theorem, else regular reg is dense, else zero-dimensional Z is dense. And you can argue about these maps. And this never made it into a paper because I didn't really understand properly what these inclusions mean. I mean, at least I understood somewhat what it means, but I wanted to have a bigger picture and then I didn't find it worth to publish it. But I'm gonna write, for two of these maps, I'm gonna write one is less than the other if for every clopin upset you have this containment. So what we have easily is to see, we can easily see is that algorithmic part is contained in the continuous part. This corresponds to the fact that algebraic frames are continuous frames. And the zero-dimensional parts inside the regular part, that's because zero-dimensional frames are regular frames. What I wanted to kind of know, when do other inclusions hold? Or what does it mean if con is contained in regular and when are certain things equal? I have a partial answer to this. So these arrows show containment. So AUG is always contained in con, Z is always contained in reg. So when the frame is compact, 0 will be contained in AUG and reg will be contained in continuous. And I always wondered, how do I go down? What I saw is that if you're regular, the continuous part is contained in the regular part. So I thought that regular is kind of an analog of compact. So if I'm regular, this should go inside of here, but that did not happen. It's actually more like, because this is the regular part, once you're regular, this will go inside of here. And what happens here is if this is zero-dimensional, the algebraic part will go inside the zero-dimensional part. And now if you think about it, if you're compact and regular, compact regular frames, these two things will coincide. And if you're stone, that means you're zero-dimensional compact, the algebraic and the zero-dimensional part will coincide. You can also ask, when is con contained in AUG? That just means it's algebraic, and when is reg contained in Z, that just means it's zero-dimensional. So why is this a partial answer? Because if you're compact regular, these coincide, but these coinciding is not enough for the frames to be compact regular. And that was also always something that bothered me, that it doesn't work that way. I think what I've showed is that if the frame is spatial and these two are equal, then it is a compact regular frame. So you need to kind of add spatiality to make sure that these inclusions give you the corresponding property. But yeah, I like this diagram, I made it yesterday. I'm proud of it. But I guess I have to move on. So I wanted to point out some other things. Instead of talking about these maps, other ways to kind of see how these spaces behave. And we already saw spatial means the localic part is dense. Compact means min x sits inside the localic part. Just thinking about regular is that it means that the localic part is inside the minimum. So if you're compact regular, the minimum is exactly the localic part. And something that I find interesting about stone is that these Clopen up and down sets, they become exactly the Clopen-Scott upsets. So what is interesting is that, so if you have a Clopen-Scott upset, it will always be a downset too. And that's I find it very rare that upsets just turn into downsets like that. Probably going too fast today. Are there any questions so far? And I guess I can end earlier. So let's talk about this last section. So we have this adjunction, right, from frame to top. How do I realize this adjunction through Priestley spaces? If I want to factor through Priestley space, how do I get this done? So I want to have a function from these L spaces to top. And we already know that I kind of want to work with this localic part because that's the space of points. So I wanted to find a functor that maps the space to its localic part. And I also have to think about maps. So the natural thing to do is if I have an L morphism from one L space to the other, I just restrict it, and hopefully this restriction works out. So in this lemma, I'm going to show that at least it is well defined. I'm not going to show it's continuous, but I'm going to show it's well defined. So if I have a localic point here, I want to move it here. So say I have a localic point, I'm going to look at this set, the downset of the image and then the complement. It's a very similar idea that we had before. What happens then is that y is not in the F inverse of this, because y is in the f of y is in the downset of f of y, so it's not in the complement, so y is not in here. That means downset of y intersection, this thing is empty, because u is an upset, inverse of that is an upset. If y is not in it, means its downset doesn't hit it. But because it's a localic point, this is Clopen, so in particular it's open. The open set does not hit it, so it's not in the closure of that thing. But what did L morphisms do? They commute with closure inverse on open upsets, so I can pull the closure inside. What that now means that f of y is not in the closure of u, which is equal to this thing. What that means that u is the closure of u. Because if it wasn't, we would have that f of y is in the closure of u. Because if there's any point in here that's not from here, that would mean they're in the downset of fy. And if you're in the downset of fy, you will pick fy in the upset. So that's why it will pull this inside, and then they have to be equal. So this u is closed. That means f of y is a localic point. So this is indeed a well-defined restriction. You also have to show it's continuous. That's not too bad. I had another slide here that I removed. Maybe I will mention it later, but we had all these characterization of L spaces and which frames they correspond to. And we can define these kind of categories. So con L pre's is the category of L spaces that correspond to continuous frames. Compact regular frame L spaces are category of compact regular L spaces, and so on. Do it for all your other favorite frames that we have described. And the good thing is Y restricts to these equivalences between, for example, continuous L spaces and continuous frames. I'm kind of brushing under the rug that the morphisms have changed for continuous frames, because usually we talk about proper morphisms there. And that all works out, but you have to describe the Priestley analog. Why did I pick out these two categories? Because there's two well-known dualities with these. You have the Hoffmann-Larsen duality between continuous frame and locally compact sober spaces. And the Isler duality between compact regular frames and compact Hausdorff spaces. So doing it through this factoring to Priestley gives you alternative proof of these dualities. And it shines some new light on them because we can understand them, how they work through these Priestley spaces. So this is my more or less last slide. But we have showed that frame is equivalent to localic Priestley spaces, and we have this. When I did this first, I didn't really understand the functor back. But this is part of an adjunction. So you get this adjunction between frames and tops. And you can restrict this to spatial frames, spatial L spaces, and sober spaces. So the slide that I skipped talks about this. Because one thing that I wanted to show is that the functor Y is full. So when I have two spatial L spaces, and I have a map between the localic parts, I have to extend it to a map between the L spaces. And that was quite a headache. I looked at the proofs, and it's like 2 pages to prove that in my paper. I didn't think it would be that hard, but when I did the proof, that turned out to be very hard. But it was too complicated to put it on a slide. At least I didn't really understand a good way to make it easy to like comprehend. I wish just one point out that was a really annoying thing. But it does work out in the end nicely, and we can stick it to continuous frames, algebraic frames, stably continuous frames, arithmetic frames, stably compact frames. I want to point out that this is the Hoffmann-Larsen duality. And we can go all the way down. Here we have Isbell, and I will end with stone. So you have stone frames equivalent to stone spaces through stone Priestley spaces, whatever they are. So to summarize this workshop, I hope I've showed that Priestley duality is this kind of bridge between spaces on one side and algebraic objects on the other side. So for us, we talked about frames. I guess I messed up. We talked about L spaces and frames. So in this sense, Priestley duality gives you a geometric perspective of frames. All frames, whether they have points or no points, through Priestley duality, they get some points. But it had a cost. So I kind of made a deal with the devil to do this. I lost the constructivity that is so nice about point free topology. Because for Priestley duality, I need the prime ideal theorem. So it's not the worst, it's not axiom of choice, but it's pretty bad. It's pretty non-constructive. But nonetheless, it has some applications, it has some fruitful results. It gives you some insights. not only point-view topology, also other areas of mathematics, logic. I run out of examples. So I like that this is my last slide. Before I finish, I want to thank some people. First of all, I wanted to thank the organizers. Because without them, I would probably not be here, because they have given a lot of support to me and Ranjita. I want to thank Angel, and I don't know if I see him, but without Angel, I would not be here. I also want to thank the students for making me feel welcome here. I was trying to remember all your names. I can try. So you have Carlos, you have Armando, Alicia, Jose Roberto, Pablo. Is Pablo here? He's not here. But I want to thank Pablo too. I think that's all students. I think I did it right. But I'm very grateful for them making us feel welcome here. And I want to thank my advisor Guram for collaboration and advice in this area. I want to thank Manjita for support.
Is there any question, Sebastian?
And can I wasn't done thanking people.
Oh, sorry.
I wanted to thank everybody here for like making a warm atmosphere. I feel really comfortable here. That now you can. Go ahead.
You are very welcome. Is there any question for Sebastian? Do you like the workshop? That's your question.
Yes, I don't have any question. I just want to thank because it brings a very interesting perspective for what I'm doing. I come from more a topological perspective, a topological background. I do not work with models or R models, all of the things that you see here. But these Priestley spaces, I was not aware of them, of their existence, and it looks very promising. I work with some kind of convergence space without points, and this looks very promising. Thanks.
You're welcome.
Thank you. Any other comment?
Thank you very much. A nice workshop. Can I take a photograph of the three-dimensional diagram, colorful diagram?
Sure.
We have another comment.
Until last night at 1 a.m. I was making this.
It's more a question. In that diagram, the functor on the top, do you know if it has a joint left or right?
I don't know left or right, but it has an adjoint. So the way you can make this adjoint is so if you start with a space Z, you can look at the frame of opens, and that has a Priestley space. And this goes there. As it was pointed out, that is not a continuous map, but this is how you go.
Thanks.
So that's you assign Z to this Priestley space. And the maps will be exactly the same problem I had to show that this is full. That's how you will map. So if you have two maps, or if you have one map, right, I need to extend it to this. But that is the headache to make this map. But that is what the edge joint is.
Okay, thanks. Is there any other question or comment?
Do you know if anything interesting happens if we take compact algebraic frames?
Compact out of algebraic.
Yeah,
frames?
algebraic frames that also happens to be compact.
Without arithmetic.
It goes to arithmetic.
These are compact arithmetic frames, right?
Mhm,
So you want to have algebraic frames that are compact.
mhm.
I don't know if anything interesting happens, but you can do it.
Okay.
It's just not a category that I have looked at.
Ah, well, thank you.
Anyone else? Well, thank you, Sebastian. We have a coffee break. Half hour.
We will continue with the second workshop given by Ranjita. And thank you.
So I would just like to recall some of the definitions we discussed last time. Hausdorffness, because now we have Hausdorff in empty algebras. I'm gonna exploit it more and find some results what we get in topological spaces in empty algebra setting, because Hausdorff condition is not that easy in frames. So now that we have, I'm just gonna show how all the results we get in topological spaces, we can get it in empty algebras too. So just to recall what it actually was, an empty algebra is Hausdorff if the elements of the form meet diamond box C, such that A is below box C, join generates M. These kind of elements are join generates algebra. And okay. And what was locally compact? Locally compact was where every open can be written as join of opens such that V in this relation with U. It simply means that you have a compact element in between them. That's what it was. That's locally compact. And then just to give a gist, if T4 is normal algebras, just like how in topological spaces, normal spaces are regular are T2, we have the same here. T4 algebras are T3 algebras, T3 algebras are T2, T2 are T1, T1 implies T half implies T0. It's straightforward. And this particular result, I put it here because I'm going to use it later. If M is a sober T half algebra, M is spatial if and only if opens of M is a spatial frame. I'll just use it, so I just put it there this as a recall. So we were from the very beginning curious, when is this empty algebra spatial? Because in continuous frame, in frames, moment you are continuous, it became spatial. Continuous frames are spatial, but unfortunately we didn't have that here. So we had to wait till here to get the M is spatial. We had to go to locally compact Hausdorff, which is very strong to be. But for now, this is what we have. We should have locally compact Hausdorff, and then we get M is spatial. I just put the proof because it's pretty straightforward. If M is Hausdorff, it is sober. I did put this in one of the slides when we discussed about Hausdorff. And then, since M is locally compact, I have opens of M is continuous frame. So that's what we discussed yesterday. The locally compact version of the empty algebra corresponds with the continuous frames on frame side. But we already have continuous frames are spatial frames. So moment it is continuous frame, it's a spatial frame. And then I'm going to use this result 4 to conclude that M is a spatial empty algebra. Because sober, Hausdorff also implies T half, right? T2 implies T half. So it's also T half and sober. Both of this is satisfied. And opens of M is spatial because it's a continuous frame. So I immediately get M is spatial. So this, the empty algebra becomes spatial when it's locally compact Hausdorff. And then I wanted to talk about what happens in Hausdorff empty algebra. We know in topological spaces, compact subspaces are closed, right? So this applies in empty algebras too. It's very much true. And I just wanted to show the proof of it. It looks complicated, but I'll walk you through. So I'm going to show, suppose A is not closed. I take an element which is not closed. And then diamond A is not below A. Remember, closed elements are fixed points of diamond. So it's not now, diamond A is not below A. So I'm going to rewrite it as diamond A meet, negation A is not 0. And now since M is Hausdorff, by the Hausdorff condition, I should get an element which looks like this, such that it's not equal to 0, and B is below diamond A meet negation A. This is simply from here. For a non-zero element, I can find an element B which does that, because Hausdorff algebras are generated by this elements. Now, since B meet A is 0, how did I get that? Because B is below diamond A meet negation A. B is below negation A. So I get B meet A is 0. I'm going to rewrite my B, this whole B, I'm going to replace it here, and it is 0. So how I'm going to go about this proof is, if we remember last class, I ended by showing the finite intersection property for compact elements. So I'm going to use that here. Suppose if this A is compact, this is a collection of closed sets, right? Diamond, boxy, it's collection of closed. So suppose if A is compact, the meet of A, this should have a finite subset. This particular set should have a finite subset such that the meet of the finite subset, meet A, should be 0. That's what finite intersection property is. And I will show that I take any finite subset of this set, that's not going to be true. So let's call this S diamond boxy, B is below boxy, and I take some finite subset of this S, and S is directed. What I mean by directed is that if I take two elements from S, let's say box B C1, box C then belongs to S, we know box C1 meet box C2. This is true just by the property of box. And then when I apply diamond, I get this is what I get. Now, when I take two elements of S, I meet them. There is an element below it, which is in S. Elements of S looks like this. And also this will be below B. So that's what I mean directed. When you take two elements from there, you have an element below it. That's what directed means. So then there is an element diamond box C in S such that diamond box C is below meet of T because it's directed. And now, because from here, I have this B is below diamond A meet box C, which implies that diamond A is not below negation box C. And now box C is open, so negation box C will be closed, which gives me that A is not below negation box C. What I'm doing is, suppose A is below negation box C, what happens? Diamond A is below diamond negation box C, but this is closed. And then I'll get back that diamond A is below it, which is not true. So A is not below negation box C. And then I rewrite it as A meet box C is non-zero. And then I get A meet diamond box C is non-zero because diamond box C is above box C. And similarly, I get A meet of T non-zero because diamond meet T is above diamond box C. So I took a finite subset of this set and I showed the meet of that set, meet A, is non-zero. So A cannot be compact because it doesn't follow through the finite intersection property. So that's how I showed that suppose I don't have if A is not closed, A is not compact, so all compact elements are closed. I was trying to look up the proof how it is done in topological spaces. I think it's very much different from this one. I think they use neighborhoods. Okay. So now we have another result which is true in topological spaces. If I have a locally compact Hausdorff empty algebra, they're regular. So most of my results will be locally compact Hausdorff because I get so much out of this Hausdorffness. I've added the proof for that too. It's pretty easy. Again, Hausdorffness implies T1. So all I have to show is this relation where A is relation with B, there exists a compact element in between, implies that A triangle B. If you remember, this A triangle B was the one giving us regular, diamond A below box B. So if I have open elements A, B in relation A, this relation B implies there exists a compact element K such that A is less than or equal to K, less than or equal to B. So now since M is Hausdorff, we saw compact elements are closed. So because compact elements are closed, when I take diamond on all of them, so I just get diamond A, between these two, diamond A is below diamond K, but K is closed. So diamond K is just K. Diamond A is below K and K is below B. So by this condition, I just get A is triangle B, and the regularity follows. So locally compact house of algebras imply regular. And then by that, we can see that M is locally compact house of empty algebra if and only if opens of M is continuous regular frames. So yesterday we saw locally compact sober was giving us continuous frames. So yesterday locally compact sober, here it was just continuous. Now I have made sober to Hausdorff, and on the frame side I get regular. Because on the frame side, we don't have anything to do with Hausdorffness, so I get regular on the frame side. So this is what I get. Continuous regular frames is equivalent to locally compact Hausdorff empty algebras. So if you remember all this, while all the dualities I did yesterday, for the getting an equivalence, I had to add S here. I had to make it spatial every time. But in this case, because locally compact Hausdorff was spatial, I didn't have to do that. From here on, from all the dual equivalence, from here on doesn't require spatiality. It just follows. And then the dual equivalence between the locally sober, local sober SMT restricts to Hausdorff and Hausdorff empty. And then by corollary, we can just get that continuous regular frames are dually equivalent to locally compact Hausdorff, because continuous regular frames are equivalent to locally Hausdorff empty, and that Hausdorff empty is dually equivalent to locally compact Hausdorff. So by that, I just get continuous regular frames are dually equivalent to locally compact Hausdorff. I think this duality is not there anywhere. So there is no name for this because this duality is not there. And then now, once we talk about the locally compact Hausdorff, we will talk about what happens in compact Hausdorff. As I mentioned previously, because we have Hausdorffness in my empty algebra, I'm going to use it everywhere. So now I want to show the other way. The previously, if it's Hausdorff, we saw compacts are closed. Now, compactness will give me that closed elements are compact. This is pretty much true in topological spaces, and it's going to be true in empty algebras too. So, and the proof is very straightforward. Suppose I have a closed element and I want to show it's compact. C is below join of open elements. Then I rewrite it as negation C join S is 1. Since M is compact, that means 1 is compact, right? 1 is compact. I just get the finite collection of T such that negation C join T is 1. And then from that, it just follows C is below finite number of elements of opens, and then C is compact. So this is a pretty straightforward proof. And then now I can conclude that if I have a compact Hausdorff empty algebra, compact elements are exactly closed elements. They coincide when we have compact Hausdorffness. And this is also very much true. If M is a compact Hausdorff empty algebra, then M is locally compact. It's more like everything that happens in topological spaces, it will happen in empty algebras. So now compact Hausdorffness will give me Isbell duality. I think Sebastian mentioned Isbell duality. So I'm going to get the Isbell duality using the empty algebras. So K Haus will be just compact Hausdorff, and then K regular will be compact regular frames, and then K Haus is compact Hausdorff spaces, and then we have an equivalence between compact Hausdorff empty algebras and compact regular frames. As I mentioned, we don't need spatiality anymore. Everything is spatial. And then the dual equivalence between compact Hausdorff and compact Hausdorff spaces. So from these two, we can immediately get compact regular frames are equivalent to, dual equivalent to compact Hausdorff. That's Isbell's duality. I just used my empty algebras in between to get a dual equivalence between these two, and that's the Isbell's duality. So now I want to talk about zero-dimensional empty algebras. zero-dimensional empty algebras. Before that, let me give some definitions. An element is clopen, as the name suggests, if it's both open and closed. So what is closed elements? Negation of open, right? So I just wrote an element is clopen if both A and negation A both are open. So I'm going to call the collection of all the clopen elements to be CLP of M. And what is zero-dimensional? One, I have to add this T1 algebra everywhere because I want to generate everything using open. So I'm going to add the T1 algebra. And every open can be written as join of clopens such that B is below A. Join of all the clopens. And now I say, M is stone if it is zero-dimensional, compact, Hausdorff. I just didn't include another slide because it's repetitive, but we can also do it for locally stone. Locally stone is not something very popular, but we can do that. The only change is M is locally stone. If it is zero-dimensional, locally compact and Hausdorff. Instead of compact, I'll have locally compact, and then this becomes locally stone. So on the frame side, we have zero-dimensional frames. What is zero-dimensional frames? We call an element complemented if C join C star is 1. C star is pseudo-complement. I think I used this before in regularity also. So C star is join of all the elements such that C meet X is 0. This is pseudo-complement of C. And I'm going to call the collection of pseudo-complements to be CMP of L. And then we say L is zero-dimensional if for every element A is join of complemented elements of L such that C is below A. Complemented is if there exists a pseudo-complement, this is, oh yeah. And now we call a frame stone if it is compact and zero-dimensional. So now I want to compare how complemented elements and the clopen elements relate to each other. So if I have an empty algebra and A is a clopen element, if and only if A is a complemented elements in opens of M. If I start with a clopen element, of course, A is open, negation A is also open, but negation A is the complement of A in opens of M. So, and then immediately I get A is complemented. Conversely, suppose that A is complemented, then A meet A star is 0 and A join A star is 1. So negation A star has to be negation A because these two will make it negation A. So negation A is in opens of M and A is clopen element. So this is pretty straightforward. No, so now if I have an empty algebra, which is T1, M is zero-dimensional empty algebra if and only if it's a zero-dimensional frame. So once I have the zero-dimensional and zero-dimensional frame, now I'm ready to do the stone empty algebra and stone frames. So if I have stone empty to be full subcategory of compact Hausdorff, and then stone frame, and stone is just stone spaces, I get a dual equivalence between compact Hausdorff, I get a dual equivalence between stone empty algebras and stone spaces. And I get I get an equivalence between stone empty algebras and stone frames. Again, as a corollary, I can get an equivalence between stone and stone frame. So stone frame is dually equivalent to stone. This is not actually stone duality, but it's stone duality is not the name, but because we are getting a dual equivalence between stone and stone frame, I just named it like that. I will finish very early. So now I just want to give the whole picture of what we did. So the locally compact sober was for compact house dot and then to stone. In between, I did some of them, which I didn't put it in the picture, I just skipped. But this is the main picture because this is Hoffman-Lawson, this is Isbell, and this is stone duality. These are the main three dualities, so I just put these three, but we did a lot of them in between. We did stably locally compact, we did locally house dot, we did a lot of them in between. I want to end my talk by relating this to stone duality for Boolean algebras. So for that, how do I construct this stone duality using my empty algebras? So we use canonical extension. What is a canonical extension? A canonical extension of a Boolean algebra is a pair, I denote it by B sigma and E, such that B sigma is a complete Boolean algebra and E is a Boolean embedding, which follows two conditions. One is density, that is each element of B sigma is join of meets of elements of E of B. So join of meets of elements of this embedding. And then next one is compactness. This condition is what gives us the compactness actually. For each ST in a Boolean algebra, if arbitrary meet of E of S is inside, below join of E of T, then there exists finite subset of S and T, S naught and T naught, such that this meet becomes meet of S naught, that is finite meet, and this will become finite join. These two conditions make it a canonical extension. And I'm going to use these two to get a empty algebra. So if BA is my category of Boolean algebras and Boolean homomorphisms, and for a Boolean algebra B, we just saw that B sigma is a canonical extension, and we can actually show that it is a stone empty algebra. It is zero-dimensional, it is compact, it is house dot. We can show all three for this. And the way that I define the box is just by this. Box A is join of B from B such that B is below A. So now I started from a Boolean algebra. Now I have not just an empty algebra, but a stone empty algebra just by starting from a Boolean algebra. And then I get Boolean algebras are equivalent to stone empty algebra via the functor. This is my canonical extension functor. I take a canonical extension and go from Boolean algebra to stone empty algebra. And how do I go back? I take the clopens. That's exactly what we do in stone duality, right? We take clopens to go from a stone space to a Boolean algebra. The same thing I do here. I take the clopens of the stone empty, and then I get a Boolean algebra, where clopens associate an empty algebra with its clopen elements. By doing that, I get a dual equivalence between BA and stone. This is our stone duality. Boolean algebras are dually equivalent to stone. So I go through again by stone empty. So I just want to point out something here. So this is the picture we have. I have stone empty, and from stone empty, I take clopens to go to BA, and then I take the extension to go to stone empty. But we also know how to go to stone space, right? We also know how to go to stone space. We just take the atoms. On the other way, from a space to an empty algebra, it's always a power set algebras. I just take the power set. So now I just want to, this is dually equivalent to, how do I go back and forth from here? I don't know if you have seen this before. From stone to Boolean algebra, I take the ultra filters of an algebra. This is reversed. From Boolean algebra to stone, I take ultra filters. from space to a Boolean algebra, I take clopens. I'm going to write it this way. So this diagram actually commutes. So power set of ultra filters is isomorphic to canonical extension. So whenever we think of a canonical extension, instead of thinking of it as all the complicated definition, it's just taking the power set of ultra filters of a Boolean algebra. That's all it is. That's all the canonical extension actually is. So, and that's why this diagram just commutes and we get the dual equivalence per stone. And that's exactly why this functor is useful for me because of this. And that's it. Thank you. And I want to. I don't have a slide to thank people, but I'm really grateful for everybody, organizers, and Anhel especially. I think the first time I gave my talk in my career, it was in front of Anhel, and he was so encouraging. So if I'm standing here today, it's just because of him. So much confidence and so much power to him. I have so much respect. I don't know where is he. So, but yeah. And also, of course, my mentor, Guram Bezanishvili, and my university, and Sebastian, and everybody, and also all and his students. They were so kind. I have not paid for dinner yet, like they're paying for my dinner somehow. So it's been amazing. So also I have a request, if you guys have a postdoc, I would be happy to do postdoc in the Mexico City or anywhere in Mexico. I'm in love with it. And I promise to learn Spanish before I come back. Thank you so much. Thank you.
Angel had to attend a meeting, so
Okay.
that's why
Yeah,
he's not
okay.
here. Is there any questions? No? Perdón.
Thanks. Can you show us again the first slide of today?
First one?
Yeah. Where you have a result about empty algebras being locally compact, that implies partial, I think. That's an if and only if, or
Which
yeah.
one?
Yeah, that one. Yeah, it's just one direction. Okay, if it is locally compact Hausdorff,
then it's spatial. Yeah.
The other way is not true.
The other way is true too.
It's true.
Yeah, because if I have M is spatial, opens is spatial, and no, I don't. This one you won't get Hausdorff. I have to assume that it's Hausdorff, and then from here I can get locally compact.
Interesting.
I have to assume it's Hausdorff because I need soberness to make it spatial. I need soberness, anti-half. So I have to assume Hausdorff, and then I can prove that, yes.
Okay,
So
that's nice.
Yeah.
So then you have another result.
This one?
I think that's what, but for example, in that case, that's an spatial algebra, right? Or not? No, you are not asking for compact. Yeah, just compact elements.
True.
Okay.
Without being spatial.
Yeah.
I don't have to be spatial at all.
Yeah, I think you have another one, locally compact, if and only if open of M is continuous regular.
Yes.
Yeah, in that case, we are talking about a special algebra because you have all the
correct. That's true because this locally compact Hausdorff will make it spatial automatically. So yeah.
Excellent.
But to be honest, in the proof, I don't use the fact it's spatial at all.
I know. And you have functors to go from empty algebra to topological spaces.
Yes.
This definition, how does behave under functor action?
Oh, it's the same functor. It's the same functor. If I have a Hausdorff empty algebra, the power set of, the atoms will give me the topological spaces. The only thing where it fails is normal.
But I'm asking about the definition themselves, like if you have your definition of compact on empty algebra
Yes.
under the functor.
Yeah, it is compact. Yes, that's true.
Nice.
That is true. Yeah, atoms of a compact empty algebra is a compact space.
And I suppose because
Locally
that's
compact also. Hausdorff also. Everything is true under the atoms, functor atom. Only thing which is not true is normal.
only is not true.
Normal.
Normal. Okay.
Yeah, if I start with a normal empty algebra and I take the atom functor, I may not end up in, I don't know still. I'm not
Okay.
good with it.
And I suppose the other way is true because
Other way it's true
yeah,
because it's just power
that's,
set.
yeah, exactly. Okay.
Otherwise.
Okay, that's it.
Yeah.
Thanks so
Thank
much.
you so much.
No, thanks.
Is there another question? I have a comment.
Yeah.
Later, you said that you have a duality, Hausdorff, compact Hausdorff spaces, and compact Hausdorff empty algebra, something like that.
Yeah.
In this, I don't know, this is like, it makes sense to ask, for example, in compact Hausdorff spaces, you have the sphere.
Sphere?
The sphere.
Oh, yeah.
Is someone working in how the empty algebra associated to the sphere is?
Can you tell me what sphere is? Like
A sphere?
oh, just the sphere, real. Oh,
sphere.
sphere. Oh, no.
What is the empty algebra
of
to the topology associated to
Oh,
the sphere?
no. That's a good thing. I have not looked it up. No, I don't know.
Okay, thank you.
Yeah.
Because in one hand you have the real spaces.
Correct.
So
Yeah.
what is the empty algebra which
For the-
corresponds?
Yeah. That's good. Yeah, I think, I've not thought about that. No. Yeah, that's a good question. A good comment. Thank you.
Thank you. I want to thank comment.
And you work, do you have another notion, Hausdorff empty algebras? For example, strongly Hausdorff, weakly Hausdorff?
No, like if I have an Hausdorff empty algebra, it is the opens of that empty algebra will give me weak Hausdorff frames, and it will also give me strong Hausdorff.
Okay.
Because it's exactly the same as what happens in topological spaces. The Hausdorff condition I have, it's same as in topological spaces. So because we have strong Hausdorffness, it gives me topological space Hausdorffness. It does the same with me. I mean, with this, yeah.
Thank you.
Anyone else? Okay.
I think you have already answered this, but I have to ask again. All this theory can be stated equivalently with a diamond operator?
Yes,
Okay.
yes, that can be done, but you will get coframe, not frame.
Interesting.
Because diamond goes to coframe. The fixed points of box give me frame. The fixed points of diamond will give me coframe.
Yeah. It's very interesting because I'm working in convergence with Alphonse and all this behavior it's very similar. Also, most of the properties are obtained through coframes.
Yes.
Because we don't work with open sets, but you need the idea of convergence, and that gives you some kind of closeness idea, and it works better with coframes. Yeah,
so
exactly.
For all the separation axioms, I also have dually. So we can go back and forth and work always.
Yeah, thanks.
Any other comment? No? Well, thank you very much, Ranjita. Wait. I would like to ask Sebastian to go in front. Can you? Wait, Ranjita. Stay here. Well, first, I want to thank you, both of you, for coming and give us these 2 workshops. They were really nice. Thank you very much.
Thank you.
And Angel and their students, his students, have some present for you.
Thank you.
3 days, and that to express that we are happy to having you here and learning things. And also, yeah, I think everyone is happy here. And yeah, thank you very much.
Thank you.
Enjoy.
Thank you. Thank you.
Okay. Our next talk is in 20 minutes.
I don't drink, so.
20, ¿no?
Yeah, I can share. Yeah.
We will continue with the talk. Our next speaker is Edith Vargas with the talk clones of functions and their topology.
Okay. Well, first of all, I would like to thank the organizers to give me the opportunity to talk at the meeting. When I speak about clones, I am very happy to start with the basic notions and to start really, really basic. And I apologize in advance if you think that it's very basic, but okay. So I think, I'm not sure. So I divide the talk in three parts, in three different sections, and I am intent to go or to meet the three words that in the meeting says something with algebra, category, and topology. So I will be happy if I can do it. The word that I will move, or that this talk is about functions. In general, if you have a set, a non-empty set, and you have a binary operation, it's a semigroup, provided this is associative. No? Then you have a map that is called a transformation. It's nothing else than a map from A to A. And when you look in the set of these maps, and you put the composition of the maps, one can form the semigroup, which is called transformation semigroup. You have also, if these functions are bijective, so it's called the symmetric group. And a subgroup of the symmetric group is permutation groups. But here there is another main subject that I will try, which are the transformation monoids. Here we have an example of a transformation monoid. It's a monoid that the elements are mappings. In this case, this map is the element that everything goes to zero, is the constant 0, constant 1. And we have this way to compose them, this table of the composition. We can have also other kinds of transformation monoids when the set is not anymore finite. You have the set which is countable, and you have this kind of two maps that if you see, they are in some way, the composition behaves similar to the last one that I showed, no, to this one. Well, these are examples of transformation monoids, but when I speak about clones, we have to go to a high arity. So not everything, it's a composition of one unary function with another unary function. So we are trying to use binary or n-ary functions, which is a map that goes from A to the n to A. And I will denote by OAN as the set of all n-ary operations. OA will be the set of all finitary operations. And in the world of clone theory, you are working with functions. And at the same time, what we don't realize, we are working with relations. So clone theory tried to connect operations with relations. An example, I will put some examples of n-ary functions because I will need it. One of them could be a binary function, which is only add the two elements. A ternary function could be defined as you multiply the first two elements and then you add the third one. You have special functions which are of higher arity, which I will call projections, or are called projections. Here, this element tells you which is the arity of your mapping. And this function, the only that is doing is to project in the if coordinate. So when you have this kind of maps, in order to define a clone, we need the set of all projections. I call it here I, but you can call it also I. You collect all the projections, all these kind of functions, right? And you put it in one set that I call it the A. And then the problem is that when you have functions of different arities, how you can compose them. For example, this call it first will be X, right? So you have here a function which is arity2, a function arity3, a function of arity3, how you compose them. So what you do is, let's say you have a function of arity20. So you have to have 20 functions of the same arity. And then you plug the tuple in each of the function, evaluate the tuple in each of these functions, and then the resulting tuple, it's evaluated again in the F. So in this case, what you are doing, so for example, if you have if1 composed with if2 by 1, 3, these two has to have the same arity, which is in this case, is that one. So you will plug this X, Y, and Z in each of the function. Then from the first function, you get that this is, I say, xy plus z. And this is the first coordinate. And then when you evaluate again in F1, so you are getting, so it's the way how you compose different functions from different arities, right? So now that you have that, you are ready to define a clone. The clone is a set of functions of different arities which contains all the projections and is closed under this composition, the one that I was talking here. Examples of clones are the set of all projections is a clone. Why? Because it has to satisfy two things, right? So the first thing is JA is a clone because JA is contained in JA. And because if you compose projections with projections, you obtain a projection. I will not do it here because you have to manage the indices and it will take me a little bit time, but you can do it. And the clone of all operations is a clone because contains the projections and because it's closed under composition. Yes, it's our word, let's say like this. So it's not difficult to prove that if you have two clones, then the intersection of clones, of two clones, is in general, the arbitrary intersections of clones is a clone. So how you prove it? So you have to make sure that you satisfy the two propositions. The one is that because C1 is a clone, so you obtain that each of them has the set of all projections. And because the set of all projections is in C1 and C2, that implies that the set of all projections is in the intersection, right? And then you have to prove that it's closed under composition. So you put, let's take F, which is in this intersection of RET, I don't know, N. And then you have to take U1 up to Gn elements which are in the intersection, let's say RETN, right? Because F is here in the intersection, F is in each of them, G1 up to Gn is in each of them. And because are clones, you will combine U1 up to Gn is in Cn. This index that I am putting here is only to indicate the arity of my functions. And I mean, I am doing all the steps, but if you combine this F with this G's, it's because C1 is a clone, the composition is closed, so you will get the composition from F follows from U1 up to Gn in C1, and from F follows from U1 up to Gn in C2, so it's in the intersection. So in general, the intersection of clones are clones, and that allows you to define the smallest clone that contains F as intersection of all clones that contains this F. As in vector spaces, the union of clones is not a clone. So now what I am saying is the most important thing probably or notion in clone theory is to connect one space, which is functions, with other space, which is related with relations. And a way to connect it is through this relation. And we will say that a function preserves a relation, and we will denote it by this, if we ask for a tuples in the relation, and we write these tuples as columns in this matrix. We apply the F to the tuples, and if you obtain, these tuples are in the relation, and after apply the F to that tuples, if you obtain one tuple which is in the relation, you can say that this F preserves rho. Why is important this notion? For example, because it allows you to define a Galois connection, which from the properties that it has is a Galois connection which is antitone. And you need these two operators, which will be this adjunction between the power sets of their relations. I mean, you order the relations, and you get this lattice, and it's a complete lattice, and you order the functions by inclusion, the sets of functions, and you get this complete lattice. So you can go from one set of relations to another set of relations by this applying this operator to the relations, which is telling you have to calculate all the functions that preserve those relations which are in Q. And also you have the operator of the invariant relations, which is you take a set of functions and then you send it to relations. You look for the relations which are preserved by F. These two operators, they form this Galois connection, which is induced by the triangle. And how they are working? Well, in order to go to see how the properties of these two operators, I think I will stop here to explain a little bit more what is that an element is a polymorphism or belongs to pole of one relation. So you have here an example. I mean, this example, you have three elements, 0, 1, 2. You have this relation, which the elements that belong to the relation are written as columns in that matrix. I mean, what I mean with 0, 0 in that arrangement, I mean that 0, 0 is in the relation, right? Or if I write, I don't know, 0, 1, so that means that 0, 1 is in the relation. So you have these tuples, 0, 0, 0, 1. All these tuples are your relation. This is the A to the 2. The tuple that it doesn't belong to this relation is the 0, 2, and 1, 2. So why this constant? This is the constant operation of arity 3. Why belongs to the polymorphism of this relation? Because doesn't matter what the tuple you are taking there. For example, if you take one tuple, doesn't matter if it's 0, 0, if it's 0, 1, if it's 1, 0, doesn't matter which tuple is. If you have, for example, this y, x2, y2, x3, y3. If you apply the constant 1 to the rows of these tuples, it doesn't matter what you have here. You always will have the number 1 because it's the constant 1, right? Doesn't matter what is the number that here exists, you will have always the tuple 1. So as resulting tuple, you get 1, 1, which belongs again to the relation. That is the definition of a polymorphism. If we go back, it's to the definition of this very, very basic and very important notion of connect functions with relations. Say, if every tuple is for every tuple that belongs to the relations, when you apply this F, you are obtaining a tuple that is in the relation. If that happens, you say this F preserves rho, or this F belongs to the polymorphism of rho. Here, you have that the projections, for example, the projection 1, 2, always belong to the polymorphism rho, because again, if you have this projection, doesn't matter which is the tuples that you have from that relation. Let's put it, I don't know, 2, 0, 2, 1. The projections, what I said, is only projecting in the first coordinate, so you will get the first coordinates of that tuple. And this belongs to the relation. So for that reason, the projections in general, for every arity, if you have an arity 20, you can repeat the tuples, it doesn't matter. For example, this function is not a polymorphism. This function is a unary function that this function is telling you that 0 goes to 0, that 1 goes to 2, 2 goes to 0. And then, so here, for example, if you take one tuple of the relation, 2, 1, you apply the F to that tuple, and you obtain F of 2, we say it's 0, F of 1, we say it's 2, you are obtaining a tuple which is not in the relation. For that reason, this function, 0, 2 is not in the relation, so this function is not a polymorphism. Once that we have clear what is a polymorphism, what is not a polymorphism, we can speak about these operators, which is an antitonic Galois connection. I mean, if you have a clone, let's say a clone or a set of operations, which is below to another, when you apply this invariant of this operator, what it's doing is changing the order, right? So you have it also, let me see, for the polymorphisms. So here you have, I didn't say, but the set of all clones, when you order by inclusion, you get a lattice. And in fact, it's a nice lattice. And with the top element of A and the bottom element is A. So if you have here two clones, you have here two sets of relations. One is smaller than the other. When you apply the polymorphism to that, you will change the order. So now the very important thing is here, I didn't speak about relational clones, and always it's quite funny because the relations gives you sometimes more information than the functions. But as a story, as a school, in clone theory, we don't speak about relations. We speak more about functions. So when you combine these two operators, you obtain these properties. I mean that if Q is below the invariant of F, when you apply pole here, a pole here, you will turn the container. So when you are investigate the relation between pole and inf, you obtain, for example, that the combination of these two operators gives you the properties that is a closure operator. So, and we know that every closure operator, or I don't know if we know, but every closure operator gives you a closure system. I mean, there is a way to connect closure operators with closure systems. And closure systems are only intersections that is close on the intersection. So it's somehow natural to try to connect this way of combining these two operators or these two this adjunction to get the closure system, which will be the smallest clone that contains F, and this will be the smallest relational clones that contain Q. This is the main theorem in clone theory, the main theorem in clone theory, which gives you a way how to calculate clones through this adjunction. This theorem is only for finite sets. When you are, and here I have a mistake because here I put D and this has to be A, but when you are in sets which are more than finite, you have to put here one operator, which is called the locals. I mean, you are localizing only in finite sets certain properties, but we are not going to speak about that in this talk. The other thing is about the lattice of clones. The clones can be ordered as inclusions, as I said, because the intersection of clones is a clones. This is a good candidate to say that is the minimum or the infimum of the clones, and but the union is not. So you have to close the union with this closure operator. In general, this lattice is complete and is algebraic. This is, for example, the lattice of the clones, of all clones, with two elements. When you started to look all n-ary functions only in 0, 1, you get, and you started to look at all functions which goes from 0, 1 up to 8. You get this lattice, which is was obtained in 1943, I think, from Emil Post. What are these symbols? I mean, it's a very symmetric lattice, which is dual. Because of this Galois connection, you got the dual relational clone lattice for two elements, which is the same as this lattice, but you turn it up. And in case of this GA, you have the diagonal relations and so on. What are these symbols of this lattice? For example, this T0 is the polymorphism clone. I didn't say that this polymorphism of every relation, it's a clone. One can prove that the polymorphisms of relations are clones. And if you look at the polymorphism, all the functions that preserve only the 0, this is called T0. If you look at the polymorphisms that preserve 1, this is called T1. M are the sets of functions which are, it's called monotonic. So what I mean with monotonic is that if you have tuples, these functions are of arity n. If you have tuples x1 up to xn, which are less or equal y1 up to yn, after you evaluate the functions in these tuples, the order is preserved. So this is one of the maximal clones, or what is called the coatoms. This lattice is atomic and coatomic. You have 1, 2, 3, 4, 5, I think, maximal clones and seven minimal clones in the two element sets. So now you are asking what is happening in the three element sets. Well, in the three element sets, the lattice of the clones equals the continuum. I mean, the cardinality of the lattice of the clones is equal to the Aleph norm. So that means that to describe that lattice is hopeless. I mean, it's more than 30 years that the people is trying to describe that lattice, and they have done only special cases if the function is self-dual, if the function is monotonic, if the functions are like this, they are cutting like the lattice. I read that all the lattices that we study are inside this lattice. Well, all the complete lattices. What else I can do? Or I can say, now come the part where I enter in the topology. So why I came to that problem, I will state that problem, because when I was doing the postdoc with John Trost, he's a specialist in model theory, which is, I am a specialist in universal algebra, which is one step to model theory. So what is a universal algebra? Is one set with functions, and if you add somehow formulas to that functions, you are in model theory. So when I came to him, he presented me a very nice and difficult problem, which takes me more or less more than 3 years to solve, which we will start with this warning. Some model theory is involved, but the warning is that I am not a model theorist. So I will tell, not the probably standard definitions, I will tell what I have learned in order to come to this problem, right? So it is natural to ask how much, if you have a relational structure, I mean, if you have one set and relations of them, is how much of that structure is in the automorphism of that structure. Here, in model theory, what is important is to study structures with at least cardinality Aleph norm. When we have this structure where the cardinality is the same as the naturals, and you have something that is called omega categorical. What is omega categorical? Omega categorical, how I understood, the most easy way to how I understood it is a countable structure where if you have an isomorphism of finite sets, you can extend it to an automorphism. That is called homogeneous. So an omega categorical structure is an countable homogeneous structure. Or another way to see it, there are a lot of characterizations, but another way to see it is always in model theory, when you have a model, a relational structure, you have a theory in that model. If it's omega categorical, all the other structures, all the other structures of that model from the same theory are the same. I mean, are the same up to isomorphism. I mean, there is only one structure, the structure, if that structure is omega categorical. It's like they call it Fresnel limit. If you see the class of all, for example, finite linear orders, the Fresnel limit of that class, the omega categorical class, is the rationals with the less. This is an omega categorical structure. If you have, for example, the class of all finite graphs of nodes with edge, and you look in the Fresnel limit of that class, that gives you the graph, which is the Rado graph. And this is also, well, depends here. This is also an omega categorical structure. Well, it's everything what I have to say about this. So Wilnar Bisky says, if you are able to prove that these automorphisms of structures are isomorphic from the permutation groups, so you can say something about the structure. You can say that the definable sets, I mean the sets of solution of the formulas in one structure is the same as the other. And this is really strong in model theory. It's what everybody is looking for. So I don't know my structure, or I have something that is definable. I know automatically my structure because I know the solutions for the formulas. So the thing is that what is happening? You have an automorphism of a structure which has cardinality aleph north. How much you can recover from the automorphism to the structure? I mean, you can, this automorphism, you can see it as abstract group. You can act the automorphism group in the group. This is a permutation. You can put it to the automorphism of one structure. You can put it a topology. Which topology is the natural one that they have. They have this topology that is called the pointwise convergence topology, or that is called the Tikhonov topology. And when you go from here, this class is contained here. When you are here, you are asking if they are isomorphic as topological groups. I mean, if open sets are set to open sets and you have this continuity, right? Homeomorphic. And then you can go to the permutation groups. And now the question of reconstruction is, if you have an isomorphism between two automorphism groups, can you say that this isomorphism is an homeomorphic? I mean, can you is so strong this isomorphism between two groups in order to say it will be an homeomorphism? That is called automatic continuity in terms of groups. But why I came to this idea is because, well, why I came to the problem is because John was interested not to study this question about if you have an isomorphism between two groups, this isomorphism is an isomorphism as topological groups. He was trying to see it in terms of monoids. And because I am doing clone theory, we wanted to do it also for clones. If you have an isomorphism from clones, that is so strong to say that it is isomorphism from topological clones, but I have not saying which is the topology. I have not saying, I will say it. So what I will need functions from that preserve the structure from the structure to the structure. Here the structures are only, for example, this kind of structure, which is one set with relations, yes? And these are the endomorphisms. The endomorphisms of A and the set of all of these kind of functions. We have the polymorphism. You already know this because I was trying to explain here what was there. And the story from the studies, you have a set. If you equip this set with the discrete topology, you become the set of all functions that goes from A to A. It's a product space, and it's equipped with this Tikhonov topology, right? So what you are looking for, the first thing that you have to do in order to solve this kind of question is to see which are the open sets. And the open sets here will be functions that coincide with other functions in a finite set. These are the open sets. For example, here I have an example. You have a finite set, A1 up to AN, right? And functions that fix these finite sets, call it UA, that is sending A1 to A0, but is fixing A11 goes to A01, A12 goes to A02, and so on. So the basic open set will be these functions that coincide with the other functions in finite sets. Are functions of this way, F from one element to another. The set of all this, these are the basic open sets. And topological, in general, topological monoids are now the monoids with this topology are called the topological monoids, and they carry this natural topology that makes the composition continuous. It's like in the same as in the groups. they carry this topology that is pointwise convergence topology, which makes the composition continuous and the function and the inverse is continuous, right? So you can see it, every monoid of this as a transformation monoid from this topological space. And let's see, for example, you have an isomorphism between these two monoids. If you see how is the isomorphism, the identity goes to identity, C0 goes to A0, C1 goes to A1. And you would like to prove that open set from 1 goes to open. So let's see how is an open. Here I put an example of an open set in these monoids. Open sets, we say that are those functions that coincides in one finite set, right? Here my finite set will be only the set that contains the 0. So let me see how much time I have. Okay. Here my finite set is the set that contains the 0. So you are looking for functions that 0 sends to 0. I mean, that is equal in this finite set, right? So the open set are functions that in this monoid that 0 go to 0. Okay, those functions are the identity. The identity sends 0 to 0, and C0 sends 0 to 0. These two elements are my open sets in this topological monoid. Then, because the C0, the identity goes to the identity, and C0 goes to A0, this is still being an open set, but now in MB, right? But here, I would like to emphasize that here, this example I believe, because I have a really struggle, I will say later why, because the monoid has something that in model theory is very required, which is quantifier-free elimination. I mean, if you have a function that you want to say this function is constant, in the monoid, you say for all x and y, if the fx is equal fy, you will say that f is constant. Right? F is constant if this is satisfied. But in the monoid, you cannot avoid this for all existent quantifier. That means that you cannot always will be able to describe constants, especially in monoids that doesn't have constants. And this has to do with interpret the structure in what you want. And here is an example where this isomorphism between these two monoids is sending to constants to no constants. And that is very important. So how are the closed sets? The topological closure, here there are a lot of steps that I didn't put, but we can prove that the topological closure of the closed sets in these transformation monoids are those who can be written as endomorphism of some relational structure. Now you know the open sets, you know the closed sets. Also, this topology, this Tikhonov topology, come to clones. I mean, it's the same, so that the basic, and I should put it, and I forgot it, the basic open sets here are Fs of RETN that coincides in finite sets. I mean, but in the last slide, I make a proof that you can get the taste of how to prove things in this topology. Well, now we have the closure, and now come the question. When I came, this question was given by John. See, he says, okay, if we can reconstruct the canonical topology, he says, I will do the monoid, and you do the clone, and how we can do it. So this question can be established in this way, and come I think the paper was published in 2016. But we have a previous paper from 2015 and says, you have a monoid and it will have reconstruction if for every other monoid there exists an isomorphism between them, there exists another isomorphism which will be homeomorphism. And automatic homeomorphicity is a property that says if you have an isomorphism between these two closed monoids, this isomorphism has to be continuous and has to send open to open, and the inverse has to send open to open. It has to be continuous and open. So what he's saying is reconstruction tells you if you have this isomorphism as transformation monoid, algebraic isomorphism, you are asking if there is another that is not only algebraic, it's also topological isomorphism. This is reconstruction. This is the definition of reconstruction. And the definition of homeomorphicity tells you if you have this isomorphism has to be the one that sends open sets to open sets. So the situation is that if you have automatic homeomorphicity, you are proving reconstruction. To that time, some monoids that we knew that has reconstruction or that they could prove automatic homeomorphicity were all the functions which were injective from the natural numbers with equal, the random graph, which I will not say specifically what is the random graph, but I tell you that is the big graph, which is the limit of all graphs which are finite. Erdos, I think that he studied this random graph with probabilities and so on. What we did was to find the automatic homeomorphicity or the reconstruction of these two structures. One is more difficult than the other. This one is easier. This one is very difficult. And why this one is easier? Because you have here the equality. And the equality, if you have the equality or equals in your relational structure, you are able to interpret elements of your structures are the ones that you want that you are studying. And if you don't have that, it's very hard. It took us a lot of time to get the automatic homeomorphicity to here. So the motivation of course comes from the groups, right? The groups have something that is called small index property. If you calculate the index of an automorphism group, and this is small, yes, then you will say that this group is open. That means that if the index, is small, it contains this pointwise stabilizer of finite sets. If you have these properties, you can say that this isomorphism between two groups is continuous. If you have this property, now you have to prove that property. Lascar, which is a paper which I really recommend, it's in French. I don't know French, but he writes it very, very nicely. And he proved, I think that is one of the most strongest results in this topological group area, which is he's saying, okay, once that you have continuity, you have homeomorphism. And once that you prove me that this continuous, the openness is for free, so you have an homeomorphism. We want to use small index property, but the small index property is working with index, is working with classes. And in clones, we don't have this kind of index. And in monoids, you don't have index. So you cannot use this strategy. So index, small index property only makes sense for groups. But automatic homeomorphicity is available for endomorphism and for clones. So why is so important that? Because thanks to Laskar, you can go to Laskar and the small index property. If you have this automatic homeomorphicity, is automatically tells you that if they are isomorphic as groups, they will be isomorphic as topological groups. And thanks to Ziegler and Albrecht, they told us if they are isomorphic as topological groups, they are bi-interpretable. I don't know if you know what is bi-interpretable, but it's only to say that this structure will be the same as the other structure through one quotient of some things that is called imaginaries, but it don't make sense here to see it. But let's come to the two proofs that I have in order to get this feeling how to prove these things, right? So what we would like to prove? You have a structure. You have this closed monoid, and this monoid contains all unary constants. Right? This monoid contains this kind of constants. CA1 of X is A. So you would like to prove that if you have, an isomorphism between these two monoids, this isomorphism is open. Because what you want to prove is an homomorphism. You want to prove since opens to opens and the inverse of opens is open. So let's start with one open set. This is a basic open set of functions which consists in these two finite sets that sends A to B. This is an open set. But you have here in this structure something that we don't have in this structure. In this structure, you don't have constants. Why you don't have constants? Because you have, for example, 1 less than 2. If you apply the constants 3 to 1, we say that, 1 less than 2. We say that we will put it as a tuple in one arrangement, which is a matrix. So if you apply C, let's say 3, 1, C3, 1. This is because 1 is less than 2. It's preserve this the relation, but when you apply the C, you get here 3 and 3, and you cannot say that 3 is less than 3, right? For that reason, this structure doesn't have constants. And if you don't have constants, you cannot interpret the elements as a function, because we are considering here only functions. So because this endomorphism monoid contains constants, we can make this step. 1A, you can put it as a constant A, and 1B, you can put it as a constant B. This is the main trick of this thing. If you don't have a way to have constants, you don't have a way to make this step. And the other is straightforward, because you apply psi, which is this monoid isomorphism, to these elements, which is the psi to these elements is applied psi to F, such that the F's are in the monoid, and F of C of A is equal to C of B. We apply the psi to here. We are applying here that psi is injective because it's monoid isomorphism. We are applying that is an homomorphism, so that you can separate here the functions. And you are applying that is surjective. I mean that this element has one element in the codomain. And again, we have here something, you have psi of a constant, but now we have the big mountain that is telling you that not in all monoids, constants are sent into constants. We have seen one example where one constant is not sending a constant. So we cannot do this step. At least we have, if we can do this step, the first time that I did this proof, I was very happy, no? And then I show my collaborators and they say, because here there is an example and we have to build that example that constants are not going to constants. So you cannot say, yes, it's open and I have now an open set. So what we can do it, we can go one step higher, where is in clone theory. So you have a clone, and assume that the clone contains all constants of all arities. And if you have a clone isomorphism, I have not saying what is a clone isomorphism, but a clone isomorphism is like the monoid isomorphism. Identity goes to identity. Here, projections go to projections. Functions of the same arity has to go to functions of the same arity. And the composition has to be preserved. I mean, if you apply psi to F, U1 to GN, yeah, you have to have, this is psi F, apply to psi U1 to psi GN. That is preserved. It's like the homomorphism in groups or monoids. So now, if you restrict this clone isomorphism to the unary part, I mean, you are in the clone, you restrict it to the monoid part, and this restriction maps unary constants to unary constants. Oh, well, when you go to the clone, when you restrict to the monoid part, there you can guarantee that constants go to constants and n-ary constants go to n-ary constants. Why? Because I remember that when I took a class with Raji, someone who knows Raji, he was telling me, Edith, the most difficult structures that you can study are the ones who are the easiest ones, because you don't have a lot of things to manage. For example, in groups, you have the inverse, and that opens you a lot of way. But in semi-groups, in monoids, you don't have that. So you have to deal with it. You have to deal, for example, with monoids, that you have this equation that we say that in monoid, a constant, F is constant, if it's satisfying this equation, right? This, we have to interpret it in the monoid, in the clone theory. So how you make this interpretation? So in clones, what you have available? Projections. So you are going to emulate these equations with projections. How you do it? If you say for all x and y, and okay, you compose F with the first projection of x1, and this gives you the F with the second projection of x1. This kind of tricks, you can do it in the clone, and you avoid this for all. I mean, you are getting a constant down, going up. I don't know if you have done this kind of exercise in linear algebra, that if you go to one dimension higher, you can see better things than if you are down. Well, I have an example in my course that is really nice, because when you go to dimension 4, you can see things that you don't see in dimension 3. Here we go one step forward. We go to clones in order to get something that we want in monoids. So once that we are able to interpret this as them, you apply psi, or you apply this restriction to the equation, because projection goes to projection, because this is an homomorphism, separates functions, because this is equal to this. Again, we can separate them, and because projections go to projections, here, this equation is telling you that a constant operation is sent to a constant operation in the monoid part. So it's what we want in order to get openness. And a trick to go, for example, from one unary operation to 120 operation, it's a way that you compose the unary operation with one projection, the one that you want, and you get the function that you get in the arity you want. So the second part is, once that you are sending constants to constants, you send n-ary constants to n-ary constants. And it's only using this trick that is used in clone theory. If you want to go, you have a unary operation. Here, I almost finished, I think, but you have a unary operation, a constant unary operation. You compose with, I don't know, you want to get an operation which is arity 20. You compose with one, I don't know, x20 if you want, or x17, will we see. And you compose with them and you will get this operation of arity 20. So you go from one arity 1 to one arity 20. Is one of the tricks that we use in order to go from arity 1 to higher arities. And using that trick, apply the clone isomorphism because it's the clone isomorphism sends projections to projections, because in the arity part, in the unary part, this clone isomorphism coincides with psi. So this is psi, so that's telling you that you are sending one constant to one n-ary constant. And once that you can do that, you can prove openness. So we were able to prove that this clone, that this monoid has automatic homeomorphicity. That means that when you have an isomorphism from this monoid to another close, has to have the same cardinality, right? So it could be A, doesn't matter, right? But here the relation is different. When you have this isomorphism from here to here, you can recover the topology. This is what we proved. We also did it for the endomorphism Q less. And for the clones, I only got it at the beginning for whole Q less equal. And 2 years later, we got it together with Mike, but making another kind of reconstruction, whole Q less. And well, here is how we did it, but I think that I will stop. I really thank you for your attention, for carrying with me. I hope you like it. These are some of the reference. I wrote a short introduction to clone theory in Spanish with a student, which is appearing in the 78 miscellaneum. Is available in the internet if you want to read it. And I have one example of our paper if someone wants it and is interested, is for you. I only have one because they give me 3, so but so I hope you enjoy.
Is there any question, Freddy?
Okay, but there is no question. I don't know how to react. Okay.
Thank you, Eddie. Now it's break lunch, and we will come back at 3 p.m. We will continue with the workshop given by Juan Omar. Thank you.
Thank you. So, well, we will discuss what we saw last time, like quickly, and we're almost there. We're almost getting to the interesting part of this theory. But yeah, just let me tell you again what TT category is. And as we define it, it's a triple, which consists of a triangulated category equipped with a symmetric monoidal structure that we call it the tensor product, and with a monoidal unit, which is a distinguished element of the category. And we ask these two structures on our triangulated category, or on our category actually, to be compatible in the following way. We ask the functor that is obtained by tensoring by the left with X and tensoring on the right by X to be exact functors for any X in our category. And we also ask like a bit more of information, like how these functors or how the natural isomorphisms that we obtain between the suspension of an object tensor, the other, relate with the double suspension of a tensor product. But well, just to recall some of the examples that we saw last time, I guess one of the relevant ones is the bounded homotopy category of projective R modules, right, for our ring R, or for a commutative ring R. And in this case, the tensor product was given by the tensor product of complexes. And the monoidal unit is the ring viewed as a complex concentrating degree zero. The second example that we saw yesterday is the stable module category for a finite group G and a field of characteristic P dividing the order of the group, which was constructed as a category of finally generated KG modules, where we mod out the projective KG modules. And in this case, the monoidal structure is given by the tensor of vector spaces, but where we equip this tensor with the diagonal action of T. So in this case, the monoidal unit is just a trivial representation. So use K with a trivial action. I will include another example just because it will be not that far from the stable module category. So one more example is the following. Again, in this context of the group algebra, one can also consider the bounded derived category of KG modules. Finally generated, that's why I'm writing this with small m. And in this case, the monoidal structure is given again by the tensor, the left and right tensor product, but again over K. And again, we can equip this with a diagonal action of K. So this turns out to be a TT category. So there is a difference between this category and, let's say, the category dperf. Oh, sorry, I'm writing this again. KB approach of KG, since the tensor product is different. So here we're considering the tensor product over K, and let's say in this case, in the case number one, even when this is commutative, so we can apply example one. So in that case, it should be the tensor product, but over KG. So it's a huge difference between these two categories. Just keep that in mind. So for any essentially small TT cat, we saw that we can construct out of it a hidden frame that consists of radical TT ideals. And in order to describe its points, we introduce the Ballmer spectrum of K as a set of our prime ideals in K, right? And we give a topology on this set by defining this support of an object as the collection of all primes such that X is not in P. So these guys will determine a basis of closed subsets for a topology on spec of K. And with this topology, we call this spec of K the Balmer spectrum. So here's a proposition. I will not prove this, but it's something that it's not super hard to check, is that with this definition, the Balmer spectrum of K is a spectral space, as was defined by Sebastian. In this, well, in particular, this collection of open subsets forms a basis of quasi-compact opens. Oh, yeah, let me clarify. I say quasi-compact, this is compact. It's just because, I guess, force of habit. I use a quick reminder of what a support datum is on a triangulated or tensor triangulated category K. And it's just a pair consisting of a topological space X, a map sigma that goes from the objects of K to the closed subsets of X, satisfying these properties. I mean, I will not repeat the properties. You can, I will stop for a few seconds so you can just take a look again. And I'll decide to include here, again, these properties because I'll come back at some point. So it will be handy. Okay, I think it was enough. So in particular, one of the exercises for of last time was about showing that actually the spectrum, Balmer spectrum, together with the support, defines a support datum on K. So now it turns out that this support datum is final on K. What it means to be final for a support datum is that whenever you have another support datum on K, then there exists a unique map, right? A continuous map from X to the spectrum, such that you can relate the two support datums in the following way. So this equation holds for any element in your category K. So this is kind of relevant in the sense that, well, this Balmer spectrum was not defined just randomly, right? It was defined to be, or to be constructed in a universal way. And that's the universal property that we want. So with this in mind, let me tell you something maybe a bit more exciting about this Balmer spectrum is that if you have any subset of the spectrum, then one can construct out of this subset a full subcategory of K that I will denote K sub Y. And this category will consist of objects such that the support of each object is contained in Y. And one can verify that this is a radical TT ideal of K. So the whole idea of this, again, is using the properties of the support, we can kind of verify that this is true. So we have a full subcategory, so that's fine just by definition, but we have to check that, for instance, it's closed under cones. How we check that it's closed under cones? Well, use the property, the property 4. Now we have to check that it's closed under suspensions. Right? Well, use the third property, right? That tells you that it's stable under suspensions. And the last property that we need to check is that, we need to check that it's also thick, but that will be actually the second property, as you can see, since the support splits direct sums. And the last part is that we need to check that it's stable under the tensor, right? But this will be true by the last property. So in fact, with this definition, we can construct from a given subset of our spectrum a tensor, a radical theta ideal of category. And the whole point of this is that, well, I'm almost there. But now let me define a special class of subsets on the spectrum. And I will say that subset X is Thomason if it's one of the form, a union of subsets X alpha where each of the X alpha has quasi-compact open complement in the spectrum. So now I will pack all these Thomason subsets in this class that I will denote use Tom of K. And well, before going further, maybe you can guess, or I'm not sure if you can guess, but the point is these Thomason subsets are actually the open sets of the Hochster dual of the spectrum, whatever that means. So if you assume that your spectrum is actually an Noetherian space as a topological space, then this condition to be a Thomason subset just means there is a specialization clause, whatever that means. And now the relevant theorem about this theory is that there is an order-preserving bijection between the radicals of K and the Thomason subsets. Yeah? And this bijection is given by, well, you take your radical and you send it to the union of all the supports of its elements. And just by definition of the support has quasi-open complement. So this is a Thomason subset. The inverse is just given by, well, applying this construction, applying the construction from the top. So it's just a category supported on or Thomason subset. So, well, I don't know, but for me, this is exciting. Now you have a space that parameterizes all your radical ideals in the category. That's really nice. Okay, so let's say to finish with the comparison between the radical ideals, what we saw yesterday, and now what we saw with the Balmer spectrum, let me just remind you quickly that we define this lattice, this bounded lattice, LK, right, which was constructed out of our category by identifying objects by saying, well, two elements are related if they generate the same radical. And we equip this with the order given just by the inclusion. And the point is that one can also consider the spectrum of this lattice, which means use the prime ideals of this lattice. One can also equip this lattice with the topology generated by these subsets, well, these closed subsets, right, which looks pretty much as what we defined before. And, well, the point is that if we consider this composition, we obtain a support datum, right? But now from the spec of the lattice with this support that we define on K. Again, Balmer universality of the spectrum tells that there exists a continuous map between this spectrum of this lattice and the Balmer spectrum. And there is a theorem that says that this map is actually an homeomorphism. Well, let me move to examples, or maybe a bit of story. Well, I'm drinking water. But this part about this isomorphism, I think, was proved by Balmer in the case that the spectrum, well, with the assumption that the spectrum is Noetherian, and then it was generalized by Henning Krause, Solberg, and well, I forgot the third author, I'm sorry, but someone else to the general context. And the context is like if you have a support datum that classifies radical ideals, then it's unique. So now, okay, the example is that if we have a commutative ring R, then the Balmer spectrum of the bounded homotopy category projective R modules is just the Hochster dual of the Zariski spectrum of R. And a way to see this is that if you have the spectrum, the Zariski spectrum of R, right? You pick a prime here, and you want to compare it with the spectrum of KB proch of R. And what you do is that, well, you take the prime P and send it to the kernel of this function. Okay, proch R that goes to the localization. this will actually be promoted to an homeomorphism. The